It's 2:15. Should we start?
Yes, we can start actually.
Speakers are here, right?
Yeah.
So can
Maybe
I
I shall
streaming? Start recording. Hi, Sudhir. Can I
Streaming?
streaming?
1 second. I'm just checking. The streaming has started, I think.
Has it?
1 second.
No, it should.
But
show-
I don't see the. Yeah, it is started actually.
Yes, live YouTube. Yes. Okay, let me just start the recording and then maybe we can start.
Right.
Okay.
Okay.
Okay, let's start then maybe. Okay, hello everybody. Welcome to the second last session of this meeting. So in this session, we have 3 talks, one of 45 minutes, another 2 30 minutes. So our first speaker is Professor P. Ravindran from Math Science. He'll talk us about Higgs production resumming next to subgluons. So Professor Ravindran, over to you. Please share your screen. You have already shared. So you can start. Yeah, we can hear you. You can start. Yeah. So I'll notify you at 35 minutes. So there will be 5 minutes for questions.
Okay, so you can see the entire slide of my talk actually?
Yes, we can see the pointer, we can hear you and your slides.
Okay, wonderful. Okay, so let me first apologize for not being present in the meeting. And thanks for the understanding of the organizers of this meeting and also the participants. So let me begin by, formal thanking the organizers of the meeting, Sudhir and his team. This is the title of my talk, and I'll try to complete in time. So let me just, it's not moving. Okay. Oh, it's quite fast actually. So it's a plan of my talk. Okay, if there are glitches, due to internet connection, do let me know. So I will actually redo it. Okay, so plan of my talk is basically this: scalar Higgs, and I will also say a little bit about pseudoscalar Higgs at some point because we have done some computation in that, and there are several observables with Higgs boson, inclusive, differential, and fiducial cross sections that I will say a few words about all of them actually. And then I will also talk about a little bit about mixed QCD electroweak corrections at the lowest lowest non-leading order. Okay, and then I will concentrate more on some interesting topic, namely resummation of certain important contributions in all these computations. And this is to do with, summing up, the dominant contributions to all orders in perturbation theory. So this is some developments that have been going along with the fixed order computations. And I'm sure most of you are aware of this, named resummation. And I'm going to talk about some developments that took place in recent times in the context of going beyond Sopless virtual approximation. Okay, so where is this next slide going actually? Sorry. Fortunately, it's not going to the next one. Okay. So standard model is enormously successful. However, it is incomplete, as we all know. That's why there are a lot of topics in this meeting talking about going beyond standard model and various issues related to that. Dark matter is something that we have not understood fully, baryogenesis, strong CP problem, so on and so forth, actually. I don't have to teach you all this, and there are several solutions that have been there from my time, actually, when I was a graduate student. And solutions do exist, continue to exist, and hopefully we will have a day that we'll see all of them actually in our lifetime, and be happy about it actually. So what's the next page actually? So I'm not moving. sorry. Okay, so it moves like this actually. Okay. So standard model plus BSM, precision studies with top quark, Higgs boson, they're very important actually because of the mass of these particles, and also certain observables involving multiple Higgs bosons in the multiple bosons, vector bosons or Higgs bosons in the final state, because they are actually to do with observables with large energies associated with it, like mass or invariant mass or large PT and things like that. But because this large masses or large energies, you can actually probe the regions which can actually shed light on physics beyond standard model, actually the regions that we want to still explore actually. And in that context, not only to actually confirm that it's electroweak symmetry breaking is due to spontaneous symmetry breaking, or electroweak all these phenomena is due to spontaneous symmetry breaking, we also need to actually probe these sectors in order to understand physics that goes beyond this standard model physics. Okay, and then in that context, we need to actually have complete control of these processes, both theoretically as well as experimentally. And in that context, as theoreticians, we would like to actually study these processes very carefully, taking into account all the effects that can go into this predicting these observables. So that's one of the reasons why we are all interested in studying these processes in great detail, actually. And today's talk is about only Higgs, not about top quark or multi-vector boson predictions and so on and so forth. So the motivation is very clear, actually, because they probe regions which are actually sensitive to physics beyond standard model, actually. So that's one of the reasons. And that fits nicely with the meeting, today's meeting, actually. Of course, life is not so nice because every computation comes with a lot of difficulties. Computation wise, they are very involved. And then in addition to difficulties associated with computing these quantities in perturbation theory, there are issues to deal with various uncertainties coming from various sources, actually, and everybody is familiar with these words. Actually, this pattern distributions are actually extracted from experiments, and they come with certain uncertainties. There are also unphysical scales that enter into these computations, namely factorization, renormalization scale, coupling constant that enters into the computations are all not known, very precisely. They also come with uncertainties, masses, threshold, contributions. The last topic is something that I'm going to spend more time on it, actually. And then, of course, even when you compute things, you need to take into account various BSM models and so on and so forth. Okay, so what are we after, actually? We are after understanding this potential. Potential looks, the most simplest one can imagine, with just an harmonic term along with the harmonic one. And this problem, in class, starting from classical mechanics to quantum field theory, it's been surviving for ages, understanding this potential, and this potential is the one which is actually is responsible for Higgs, and Higgs is responsible for masses of all the elementary particles. So it's a very, very important potential, actually, in physics. And having measured the mass of the Higgs boson at LHC, we have something to say about the anharmonic term, actually, namely the lambda 3 and lambda 4 couplings, because they are predictions in the standard model. And this is very important because this is the place where we can actually really say whether this mechanism that we talk about, Higgs mechanism, is really due to spontaneous symmetry breaking, actually. So it's a prediction, and the prediction need to be checked in the experiment is experimentally, and experimentalists need actually theoretical computations to actually extract this lambda 3 and lambda 4, because they cannot directly get lambda 3, lambda 4 from the detector actually. So they need to fit with the theoretical results. So theoreticians have to work on predicting processes involving 2 Higgs boson in the final state, or 4 Higgs boson, or 3 Higgs boson, and so on and so forth. So all these things are important to actually to extract this actually. This is one of the reasons. This is the status. Of course, some of the earlier talks would have shown already. This is the status from CMS. I took it from their publication in Nature, CMS publication in Nature, about 10 years stock of what CMS could actually do with the Higgs, and the vertical line is actually theoretical prediction, and all the horizontal ones are actually from various production channels. GG is the dominant one, as you can see. It is in the top, and it's the most well understood channel that in the context of Higgs boson. And there are other subdominant channels where vector boson fusion, WH, ZH, TT bar H, and so on and so forth. Actually, as you go to subdominant ones, actually you can see the errors are big, and errors are big not just because of theory, it's also because of experiments. Okay, so this is both statistical as well as systematic errors actually. So the talk is not about the vertical line, it is about the uncertainties resulting from the predictions actually. So as you can see, the pull actually from the from the standard model is very nicely described here. This is a paper that has I think appeared in Nature actually. This is from Atlas. It's it complements what CMS had done actually. Basically, they have also done similar things, but put it in a different way. Again, it's vertical lines are theory predictions, and the systematics are also from theory. And there are deviations for certain observables. They are not just simply because there is really something new there, but it is also because of the statistics is not great actually. So these are the state of the art results, both from theory as well as from experiments on the Higgs boson actually in the inclusive channel. Very good. So what's next actually? The next is actually I wanted to say a few words about vertical line and in these plots, and also the errors associated with this. So it's all started, very long ago by Wilczek and George Ellis and Rizzo and company, who wanted to actually make a prediction for the Higgs boson. And this was the only diagram that you need to compute. And then all they need to do is actually plug in this diagram and get the cross section actually. This was 77, a little later actually, okay? And the status at 19 before COVID was actually, was this. Okay, it took, you can see how many decades actually to really come up to this. And this just tells you that how difficult these computations are. Hence, it took so long. It's not because people were just relaxing during this time. So the computations have been going on actually from my graduate time, postdoc time, and even now actually my students are working on similar things actually to really go and get results which are as precise as this actually. So this precision actually that when I'm saying actually, as you can see from this plots, that we have reached really accuracy which are really unprecedented. This is a plot from Anastasio and company in 2019, and now there are better versions actually. And this is a stock of their results actually. Okay, the results about this cross section, Partonic cross section that they could compute actually. So there are several pieces. Okay, several pieces. If you're interested, we can actually go over. The first line in this, basically the second line in the slide contains results, computed not in the full theory, but in a theory where top quark is integrated out actually. And this approximation is pretty good. And the error that you make is actually less than few percent. Few percent, when I meant few percent, it's really actually 2 to 3% actually. The estimates have been done actually in the past, and it's the most reliable approach to predict exposure at the LHC. Okay, so the first line is actually predictions from the effective field theory where top quark is integrated out. Of course, that brings you additional operators, and one can actually systematically compute the effects actually. And then the second line corresponds to this contributions that are as comparative to the last one in the first line actually. That is N cube LO EFT. N cube LO EFT is actually a minuscule contribution, and I'll tell you why that is important little later, even though it's a minuscule contribution. And when you are taking a minuscule contribution from the QCD, we need to also actually take into account minuscule contributions from other sources, like, other particles that are present in, like in the loops, like top, bottom quark, charm quark, electroweak, resonance, and so on and so forth. So there are many, some small contributions that are actually neglected when we did the first few terms in the QCD perturbation theory. Okay, now they need to be taken into account because there are also competitive contributions from the QCD actually. And all these things, are added not to just, like in alpha, this alpha QED, when people like, Kinoshita kept on adding terms, there he added terms to actually to fix, the 7th decimal, 8th decimal, and so on and so forth. Actually, here it is not about, getting, say, the 3rd decimal, 4th decimal contributions actually. So the philosophy behind computing these higher order computations in QCD is very, very different from higher order computations in electroweak sector or in QED actually. The philosophy behind is actually that we need to reduce the theoretical errors that result from various sources actually. Unlike in QED, in QCD or in hadronic physics, there are plenty of uncertainties from different sources and that enter actually, and we need to actually control them. So higher order corrections are not to get actually 3rd decimal or 4th decimal corrections. Higher order corrections are necessary to actually to actually reduce the real uncertainties, are making these predictions reliable actually. Okay, so in QED, LO corrections are most of the time reliable actually. In QCD, LO corrections are most of the time are unreliable actually. So it's a very strong statement, but one has to accept actually because of the scales that enter into this. So if you just calculate leading order in hadronic physics, I would say be careful actually, watch out. There could be large errors coming from various sources actually. That's the reason why one computes. Higgs is not the only place where we compute these higher order corrections. There are many places. So just in Higgs context, I say quite a lot about these uncertainties, but in hadronic physics, if you have strong interaction dynamics involved, beware of all these uncertainties, and you need to compute these higher order corrections. So I like to stress this point again. I've been stressing for a very long time. So theoretical errors actually are listed below. Actually, you can see the error can come from scale, error can come from PDF, error can come from this heavy top, this whenever empty corrections, bottom quark loop, charm quark loop, and then alpha S actually. Okay, these are the corrections that one is actually, and in the previous slide, this the band that you see actually. Okay, when you go from leading order to next leading order to next leading, they are all effect of this actually. So I have listed here the errors. As you can see, the errors are not small actually. Okay, this is after taking into account N cube LO. And I don't want to show what the status at the leading order or next to leading order actually. So as you can see, even though the corrections are extremely small at 3rd order, but the errors that actually, that they can actually, do away is quite impressive actually. The errors are quite small actually. Okay, so that is about QCD. And now when you are taking such a minuscule contribution in order to reduce errors, we need to also to include actually contributions from other sources. People have done this exercise for the Higgs prediction. People have taken into account electroweak corrections. Okay, it's a hard computation because it's electroweak corrections enter at 3-loop level actually, because we need to consider top quark and then this electroweak effects. So NLO means actually NLO 2 it's a first order in QED and second order in QCD and so on and so forth actually. So this is the final number from a code called IX. And you can see leading order is actually 32% uncertain actually. So if somebody gives you a leading order, which is 16 picobarn, and about 20 years before, I would have loved it, but the error would have been enormously large. And next to leading order is 42% uncertain. So it's almost like 50-50% chance that you make error actually. So that kind of results are completely unreliable. And now the status is about error is about, as you can see, taking into account all of them, is very, very small, less than few percent actually. It's less than 2 to 3% actually, as you can see. Okay, if you just sum up all the errors. So they are pretty good, and predictions are very good actually. So we have a complete control of Higgs prediction as far as the theoretical predictions. Of course, the experiments are also doing great. And I said about electroweak corrections which are minuscule, but we need to include. Similarly, there are also other sources where Higgs can be produced, like BB bar and so on and so forth. Okay, so we need to take into account all these things are taken into account, and then the vector boson fusion, they are also being taken into account very precisely. So when the gluon fusion process was going on, simultaneously other processes were also included. And in addition to this inclusive ones, there are also differential ones, because inclusive ones are actually boring beyond certain point, because they don't shed light on intricacies of the interactions actually, like what type of vertices that we are probing, what types of nature of the particles that we are talking about. All these things actually can be washed away by taking an inclusive rates, but you can actually get information about all these details about couplings, nature of the coupling with a vector, action vector, or a scalar, or whatever, and then also about the nature of the particle, spin one or so, parity, etc., etc. Actually, they can be actually probed by looking at differential distributions. One such observable is rapidity. Rapidity is not for actually to because it's something to do with the angle, so you can actually probe certain characteristics of the couplings and so on. So these observables are also looked at in great detail. Actually, people have computed them, and there are also measurements actually. Okay, one of them is the fiducial actually cross sections. I will come to that a little later, and this is one prediction on fiducial cross section from the theory from Chen group into during COVID time actually. And this is one that is compared against experiment, as you can see, even though the errors are quite large, but this is quite impressive because already there are data on this, and these fiducial predictions, cross-section predictions, are going to actually really help to probe various vertices actually. This is one thing where people looked at 4 lepton prediction from associated prediction of Z, okay, with the Higgs. Okay, so far so good, and I've covered quite a lot about what is the contributions, what are the contributions that can actually come from fixed order methodology, like add more and more terms in the fixed order computations. And of course, we cannot actually close our eyes and say that, okay, fixed order computation is everything, okay, because it's asymptotic, result. So we have got everything and go home. Actually, that's not correct, because one finds while doing these computations and looking at terms, carefully, one finds actually there are terms in the perturbative expansion, in particular for Higgs production, in proton-proton collisions. All these things are, particularly very specific to the situation that we consider: PP collisions and gluon-gluon fusion, and the energies that we are talking about, 13 TeV or 14 TeV. One finds there are corrections that we can actually, by ignorance, miss it actually, unless we look at the expressions more carefully actually. So I'll show you what are those corrections that we can miss, and that need to be taken into account actually. Okay, so let's go back to the expression that we started with. So X, if you are interested to compute, to compute the inclusive cross-section, it's, as you know, it's factorized into this PDFs times this cross-section, and I was mostly talking about the second line actually. Okay, if you look at the second line, which is, computable partonic cross-sections, using, loops and legs, of involving Higgs boson. Okay, that piece contains a very special type of terms called soft plus virtual terms actually, and you will recognize this if you compute these cross sections by yourself actually. Okay, or if you look at some papers on this topic, you can recognize very easily. Okay, so the first one is called soft plus virtual. The remaining ones actually, whatever it's not soft plus virtual, I call it as a hard one actually. Okay, if you look at the soft plus virtual term, they are actually often are distributions. Distributions, everybody knows. Delta function is a distribution. It makes sense only if you, under the integral sign. Okay, they are integrable functions. And we have seen distributions in life, in various places actually. This is very special type of distributions. We call actually plus distributions in quick quantum chromodynamics or in these higher order computations. These distributions are more like principal value functions actually, and they are well defined under the integral sign. If you multiply a test function, you get a number that is finite actually, so you don't get anything nonsensical. Okay, so these are called the distributions actually. So how much time I'm left with?
Yeah, 25 minutes or something. Sorry, 15 minutes or something.
15 minutes.
Yes.
Okay, so I'll try to finish in 15 minutes actually. Thank you. So this part actually, soft plus virtual, is something very special about these cross sections actually. Not only for the inclusive ones, you can also have similar distributions with no more variables. Instead of one variable, you have more variable. That's why I put Zi. Zi's are nothing but thresholds. Okay, they are ratios of invariant mass of the final state over invariant mass of the initial states actually. So if they are very close to each other, that means the energy that is pumped into producing these final states are very close to each other. That means the additional particles that are produced along with the set of final states that we are looking at. In the case of Higgs production, it's a single Higgs. In the case of trillion, it's a pair of leptons. In the case of 2W productions, it's a pair of 2Ws, and so on and so forth. If these two are very close to each other, that invariant mass of the energy pumped in and the invariant mass of the final observable, like Higgs or pair of Higgs, then you have a situation that the process that we are looking at will have large number of soft gluons actually, okay? Because you cannot actually control emission of soft gluons in any hadronic process actually. This will be going on forever actually. You cannot say how you stop producing gluons in the final state or initial state, because the quantum field theory will not allow this actually, because such process can take place without costing any energy actually. So the soft gluons will be produced all the time in hadron colliders as if there is a possible, even if there is no, energetically it's not possible actually. The soft gluons are very dangerous actually. They come freely actually in all these hadronic processes. Don't pay anything to them. They come actually. It's because of quantum effects. Okay, because we are talking about quantum physics, so you cannot stop them actually. It's like power productions in vacuum. It cannot stop it actually. Vacuum contains all this. Similarly, in all these hadronic scatterings, these soft gluons will be produced enormously. Even if you actually restrict your kinematics, that I give you this much energy, I look for only this, same amount of energy in the final state. Can I stop it? Actually, you cannot stop. Actually, they will be there. And these things, they actually, looks innocent, but actually they give you these divergences, these distributions actually. Okay, so these distributions that they produced, innocent gluons produced without any cost of energy, they actually can actually spoil your reliability of your theoretical predictions actually. So they're so dangerous actually as far as theoretical physics, theoretical computation. When I say dangerous, I don't mean that actually they are not handleable actually. They are easily handleable, and they any such serious things that come for free, they come with difficulties, and of course they are very, very precious actually. I will tell you why they are so precious actually. Okay, so this goes by the name soft plus virtual. Okay, so virtual diagrams are also responsible, and soft gluons are also responsible for these things. Okay, very good. So these are the distributions actually that I'm talking about. Okay, and you can also classify these distributions, in different ways actually. Okay, and I have just given you a small intro to this actually, where they come from actually. They come from two regions of the phase space. One, when the gluons become soft. Another one actually, often there are gluons which are not soft but are collinear to the final states at initial states actually. Okay, so these are two types of gluons. Okay, they come in two avatars. One called the soft ones, the other one are called the collinear ones, and both of them are actually responsible for these distributions actually. Okay, I'm not talking about the hard ones actually. Hard ones are innocent ones actually. They are also important. They cannot be ignored. You cannot ignore them actually, but you need to keep them. But the soft ones actually are extremely dangerous and extremely beautiful actually. Okay, why it's beautiful actually? Because they are beautiful for the following reasons actually. They come with some systematic pattern. They don't actually arbitrarily appear with some arbitrary coefficients in front of them actually. They come with a very, very specific type of coefficients. And these coefficients allow us to actually understand the structure of terms, not just in that particular order of the perturbation theory, but to all orders in perturbation theory. In other words, the coefficients are such that you can actually, by knowing from the lower order ones, you can actually talk about the coefficients of these terms at higher orders actually. In other words, actually, there is kind of connections between the coefficients of these distributions between various orders. In fact, actually, they are connected to all orders. For example, a statement that I can make is actually that if I know certain terms, leading terms in terms of in a lowest order or lowest next to order, leading order perturbation theory, I can actually predict the coefficients to all orders actually, because there is some underlying differential equations that allow us to actually predict. It's like, if I know a boundary condition of a, let's say first order differential equation, then I should be able to actually predict its, that's a entire function. If I actually solve the differential equation and substitute this boundary condition, that means I can get the solution in the entire entire, let's say, real axis, let's say, if it's a first order differential equation. So it's like, boundary, using one value of the boundary condition with a differential equation can actually predict the entire function on the real axis, if you assume that there are no singularities. So it's like that actually. So there is the reason behind all this miraculous things to happen actually, and the miraculous thing that happened, which can actually allow us to understand these results to all orders in perturbation theory, is simply because they take a very simple form in the soft Gluon approximation, and that leads to this. So this is how your result looks like actually. If you just keep only those dangerous and beautiful gluons, soft gluons, in particularly for the inclusive cross sections. So you can show that the corrections that one is talking about, they sum up beautifully, like the one that I've given in the first line. Actually, it's called integral representation. So it is actually this entire P's and Q's can capture the entire series of terms in the perturbation theory to all orders actually. But note that this psi that I've written down in the exponent, it contains only the information about the soft and virtual gluons actually. So they are very, very specific type of gluons. So it's like capturing certain terms in perturbation theory, every order in perturbation theory, not only first few terms, but all the terms in the in the series actually, and put them, and you can write a compact expression for these things actually. So P and Q again are perturbative expansions, and knowing P and Q to a certain order can actually predict by expanding this exponential, and then you can actually make predictions about these things. So they are very, very powerful results, because they talk about terms. For example, one day, after 20 years or 200 years, people compute, 30th term in the perturbation theory. And this result can actually tell you whether the person has computed correctly or not, actually, because if you expand and look at the 30th order term, for example, if you're looking at leading order, logs, you can actually tell whether, your grandchild has computed this quantity correctly or not, actually, So that's the power of this expression. Okay. So
you have 5 more minutes.
5 more minutes. Okay, wonderful. I'll finish it actually. Okay, so this is, the first one that I mentioned about this is called surplus virtual. This has been actually a topic of interest from the time of Sudakov, okay, very, very long ago. And then came, Sterman and company, Collins, Sterman, Mueller, and many people actually. And then after that, there are a lot of developments actually. Okay, so that's been going on actually. It's not something new in science. It's a topic that which goes by the name resummation. That means you sum up all the leading subclone contributions in a very compact way, and they contain information about these things. Okay, and you sum them up actually, as we all know, because they are all important actually. You cannot actually say, okay, I have computed two terms in the perturbation theory, let me stop here actually. That's not the correct way of doing, because if the third order term is also large, you need to actually take into account. So that way you go on and on and on, and then you need all the terms in the perturbation theory. So this expression actually provides you recipe to actually sum them up, all of them actually, and get the results. But of course, there is a systematic way of summing up all of them actually. What is new in this business actually? What is new in this business for last few years, or last 6-7 years, is actually to go beyond this surplus virtual approximation. You can ask the question whether can we go beyond this surplus virtual, and can we actually sum up the next to surplus virtual contributions, which are actually not distribution, they are like log 1 minus z type of terms actually. Okay, this was a very challenging question, challenging task actually in this area of research in large order perturbation theory, or summing up large orders in the perturbation theory. So this was a question which was actually bothering a lot of people. And recently, actually, some of us from India, and there are also groups in Europe who actually contributed to this area. And now there are very interesting results, namely, one can, there is a resummation procedure actually to sum up this subleading logs actually. We call actually NSV terms actually, next to soft plus virtual term, like leading order, next to leading order. In SV terms, soft plus virtual terms or threshold corrections, you can also have a next to threshold correction or next to soft plus virtual terms actually. And such a procedure indeed works if you carefully do. And we did it for a very specific type of processes, namely gluon initiated process, not quark gluon initiated process or quark initiated process in Higgs production actually. If you restrict yourself only to one specific type of partonic channel, namely gluon fusion to Higgs, okay, which is the dominant channel, of course, that's a very favorite channel. But if you restrict only to that, you can actually sum up the second line actually, sum over k is equal to 0 to infinity delta log, and write it as a compact expression actually. You can write a contribution to psi to all orders in perturbation. This is a very beautiful result that we obtained in recent times. And that beautiful result actually has predictions, to all orders. As I said, if you have something in the exponential, you can tell about, 1 millionth term. If suppose e power x, if I know the coefficient of x, I can predict x power, million, the coefficient of x power million. So it's like that actually. So you can predict terms to all orders and from knowing certain terms in the few in the exponent actually. So we made certain predictions using this. For example, the fourth order result, which is unknown because it's very difficult to compute. You can predict logs like log power 7, log power 6, log power 5. These are called next to soft plus virtual terms. We could predict all of them actually. And we can also resum them. Resum them means actually we can, like in threshold, in the Mellin space, I showed everything in the Z space. In Mellin space, they corresponds to these higher logs. We can sum them, vertical lines to all orders and write it as an exponential. And what is done actually in recent times is actually, when I said next to soft, basically you sum them up in Mellin space actually. So often in quantum mechanics, we think working in position space is difficult. So you go to momentum space and calculate things and then come back to this position space. Like that, you can also in perturbative computations, we find, this working in Z space is too complicated because of distributions and so on and so forth. So calculate everything in Mellin space and then come back actually. Mellin space is actually has no problems with these distributions and so on and so forth actually. You get everything in terms of some very innocent functions like log n by n and so on and so forth, but you compute them in large and limit actually. And summing up, performing this large order summation is straightforward in the Mellin space. So you do this actually in large and then this next to soft terms are the terms that look like log n by n kind of thing, log n by n, log cube by n by n, and so on and so forth. Such things can be summed up. So there are systematic way of summing up actually, leading next logs, next to soft terms, next to leading logs, next to soft terms, and so on and so forth actually. So you are actually summing up enormous amount of terms, okay, a specific type of terms, terms which go like a times log or a cube times log cube, a power 5 times log 5, and so on. So these are the vertical blocks or the ones that we sum, in every time when you go, order by order in perturbation theory. So this is just a repetition. Okay, great. So I want to show you some plot before I end the talk. Okay, I'm almost through. I just have 1 minute. Okay, so such an exercise can be actually done theoretically. And once we have theoretical expressions, we can also put it on a computer because we need to get the numbers out actually. That numbers can be obtained actually very nicely actually. So this is one plot where we have certain predictions. Okay, so it looks quite messy, but however, now one can understand that if you keep adding more and more terms and then plot it against this, scales, renormalization or factorization scales, you expect the results are less and less insensitive to these unphysical scales. So theoretically, you expect the plot should be flat. Okay, as you can see, if we keep adding more and more terms in the perturbation theory, the lines become, this wiggly lines now become, or the lines which are not, flat lines. They tend to get, each one actually is improving. Actually, as you can see, the final one, which takes into account next leading order or n cube LL term, you can see it is not flat, like a straight line. It looks reasonably flat compared to the rest of them actually. So this is the kind of improvement that you see by adding more and more terms. This is another plot where you can see adding more and more terms, how the cross section stabilizes and the errors actually become smaller and smaller. Okay, great. So I don't want to sort of bore you with too many plots. Similar exercise was done by some of us actually for rapidity distribution, okay, which involves two scaling variables, and the last line corresponds to resumming that surplus virtual terms. Okay, finally, this is what our most recent result actually for the rapidity distributions, where you take into account all the surplus virtual, exact results as well as surplus virtual and next to surplus virtual actually. So I want to thank my students who actually contributed a lot. Actually, without them, it's this plots would, or the work would not have been possible actually. So they are the driving force. So summary, I've shown actually certain well-known results in the context of Higgs prediction. They are in fact, state-of-the-art results at the moment actually, and responsible for the vertical line that you saw in the Nature publications. Okay, so they are very important, as you know. Without that, you cannot have anything to show. So it's such important results, and people have actually worked very hard to get all these results actually to make. So any deviations actually would really hint new physics. So it is a very useful result, not only to confirm, that Higgs is the standard model Higgs, and also to give room for to probe physics beyond standard model. I've also shown that fixed order computations are not all everything actually. There are very beautiful and dangerous terms that are present in this fixed order computation that you cannot leave them. You have to probe them. I have not said anything about beauty of it actually. I only said that they are dangerous. To really say that they are very beautiful, more beautiful than the fixed order results, I need one full semester course actually. This goes under the name infrared physics. And I don't have time for this actually, but I will meet you again at some point to tell beauty of this surplus virtual and next to surplus virtual and the universal structure and how they are connected to certain universal terms actually. Thanks to Sudoko, who was the first one actually who probed this, and this exercise actually continues to go on actually to probing this infrared sector of QCD actually. With that, I would like to end my talk, and thanks to the organizers for this nice meeting. I really miss the meeting as well as the food and my friends over there. Thank you.
Okay, thank you very much for the very interesting talk. Maybe we are starting time. Maybe you can take a couple of questions or very short questions. I can raise your hand if you. Yeah, Faiz, you can go ahead.
Hello.
Hello.
Just wondering if using SCIT, the soft collinear effective field here, would help improve this. I mean, have you ever incorporated the techniques of SCIT in this?
Well, in the context of see, SCIT actually is to do with the second part that I talked about actually, namely looking into the soft and collinear gluons actually, as the name suggests, So it's not about the fixed order part. Fixed order part anyway is actually, to do this hardcore QCD computations. For the second part, summing up large logarithms coming from the soft and collinear regions, there are two approaches. Namely, one approach that I talked about is the approach, which dates back to Sterman's time, actually. The second approach is the one that we talk about, soft collinear effectivity. Of course, they are very close to each other. In my opinion, I mean, there's hardly any difference as far as the final results are concerned, actually. Because soft collinear effective theory, as the name suggests, it talks about only that region, actually. And of course, if full QCD is right, soft collinear effective theory also should give the same result as QCD gives, actually. Because SCET is just a subset of full QCD. And what they claim, actually, in this resummation is that they can actually solve what they call actually Landau problem, actually, in this resummation, because we are talking about adding large, infinite number of terms in the perturbation theory. And in this conventional approach of Sterman or Collins or Catani, you take an approach called a minimal prescription or Borel summation, actually, to compute this numerically. And SCET claims that actually by their way of doing, actually, you can avoid this Landau problem or such issues. So this is the only difference. As far as the numerics are concerned, actually, if you look at the final results, you don't find too much difference, actually. Okay, so both approaches, in some sense, gives similar results, while one uses a prescription called minimal prescription. The other one uses, I don't need to use any prescription, but it is inbuilt in this, actually. So that's the only difference, actually. But as far as the physics is concerned, I don't see anything, because SCET is actually is a subset of full QCD. So I don't think it can go out of this. A subset cannot go out of a full set, actually. Okay, so it's a better, beautiful way of understanding the soft collinear physics, because it restricts only to this two types of gluons. Yeah, that's my answer, actually.
Okay, maybe you can go ahead with go to the next talk. Thank you, Professor Ravindran, for the interesting talk.
Thank you. Thank you.
Yeah, our next speaker is Professor Suvadita Bhattacharya, who is from IIT Guwahati. He talk us about probing dark matter through Higgs portal. Professor Bhattacharya, you can share your screen.
Okay. So, am I audible?
Yeah, we can hear you. Please share your screen.
And the screen is not yet visible, perhaps. Is the screen visible now?
Yeah, it's visible now. We can make it full screen.
Yeah.
Yes.
Okay.
Yeah,
Right.
it's perfect now. You can go ahead.
Okay. So first of all, thanks the organizers for inviting me to this one-day symposium on the Higgs physics, and it's an opportunity for me to listen to many beautiful talks after together covering all different aspects of Higgs physics. And I would like to talk a little bit about probing dark matter through the Higgs portal interactions. And so the first thing that we have to talk about is the connection. I mean, the connection between the dark sector and the visible sector. And what I would like to argue that the dark matter can couple to standard model Higgs boson most naturally. I mean, that's the most natural connection that one can actually have. And this interaction between the dark and standard model sector, in one hand, helps the dark matter to achieve cosmological constraints like relic density, and then show up different signals of dark matter in different experiments like collider and in direct search experiments. And however, within the very within this paradigm of Higgs portal dark matter, there are plethora of possibilities, and I would like to actually highlight some of them. In no way my choice of models are exhaustive and covers all the possible Higgs portal scenarios, but I would like to provide a series of them at least, and show that how these differences in these different dark matter models can help the dark matters to kind of provide different relic density allowed parameter space, and thereafter the search strategies in direct and collider searches can also depend on that. So this is what we would like to do. But before we go to the Higgs portal and etc., there are three things regarding dark matter that we will talk frequently about. One is the relic density of dark matter, the second is direct search possibility, and the third is the collider signature of dark matter. So I would like to first brief about these three, what exactly we mean by these three different things to start with, and then I will go to the different possibilities of Higgs portal models and how to probe them at different experiments. Okay. Oh, how do I change my slide? This way. No.
You're still in the connection slide.
Enter. No, it doesn't work. Shift.
Try clicking on the screen.
Sorry.
Can you click on the screen once? I mean.
Yeah. That. Thank you. Yeah. So okay, all right. So the first thing, that's what I wanted to talk about was the thermal dark matter, or the weakly interacting massive particle dark matter, that will be the highlight of our discussion today. And basically, the idea is, in this class of models, we assume the dark matter to be in thermal equilibrium in the early universe, and their number density evolves with what we call the Boltzmann equations. And the most simple Boltzmann equation, if the dark matter have two interaction, like two dark matter interacting with two visible sector particles, goes by this formula that I'm writing, like n dot plus 3hn equal to minus sigma v into n psi square minus n psi equilibrium square, roughly like this. And this h is the basically Hubble constant, which actually parameterizes the expansion of the universe. And now what we can do, that we can recast this number density in co-moving volume by what we call yield, where we take this n divided by the entropy density s. And we also parameterize the temperature by this variable called x and define it like m by t. And in this process, this equation looks a bit simpler, like dy dx equal to minus some sigma v into some x into x by some factor hm into y square minus y equilibrium square. Now, basically, there are two limits of this equation. Like when the interaction rate is much larger than the Hubble expansion rate, then the dark matter particle is in equilibrium. And when the rate of interaction actually falls below the Hubble expansion, then the dark matters actually freeze out. So this is pictorially represented by this cartoon figure. Like in the y-axis, we are plotting y, and along the x-axis, we have this small x variable, which I just talked about. And this falling distributions are the Maxwell-Boltzmann distributions for the equilibrium distributions. And then at certain point, we see that when the rate of interaction falls below the rate of expansion, the dark matter actually freezes out. And this is what actually gives you the relic density. And if you convert the freeze out density to relic density, roughly we get a number like this, where omega h square is parameterized by the relic density. And this is 2.4 into 10 to the power minus 10 GV to the power minus 2 by the annihilation cross sections, like sigma v into x1 going to standard model. Now, there are two important things to point out here. One is that in this kind of paradigm, where the dark matter is in thermal bath and freezes out eventually as the universe cools down, the annihilation annihilation cross section is actually, the relic density is actually inversely proportional to the annihilation cross section. And the second thing is that if we have to achieve the correct observed relic density, which is of the order of omega e square equal to 0.1, then actually we need a cross section of the order of 10 to the power minus 11 GeV to the power minus 2. And this is the order of weak interaction cross section. And that is why we call the dark matter to be a weakly interacting massive particle. So this is essentially the paradigm that we will mostly focus on. The second point was to talk about that how the dark matter can show us a signal at colliders. Now, this is a slide which I'm copying from Professor Tim Tate. And basically, there are two broad categories of dark matter signal. One where you have an extended dark sector and it actually produces some of the heavier particles in the dark sector and ends up in the decay chain to produce some dark matters with some other observable objects like leptons and jets. And this gives you like multi-lepton, multi-jet signal. And the second category is where you just produce the dark sector and you have nothing else to do, and you can radiate some initial state radiation like Professor Ravindran was just talking about. And depending on what kind of collider that you are using, there can be different kind of initial state radiations. For example, at LHC, you have gluons that you cannot avoid, which he just stressed upon. So this will give you this mono X or di X kind of signatures. However, what happens to this dark matters, because the dark matters do not have electromagnetic charges, so they will miss the detector. So basically, there are two important variables by which we can actually feel their presence. One is what is called the missing transverse momentum, and this is defined essentially by the sum over the x component momentum of the visible particles squared and sum of the y component momentum of the visible particles like lepton, jets, or photon squared and taken a square root. And although we call it missing so it is written as AT/, but this is essentially all related to momentum. And there is another variable that you can think of, which is actually missing energy, where you simply calculate the energy of the visible particles and subtract it from the center of mass energy, and that is defined as missing energy. Now you can easily understand that if we are talking in terms of LHC, then there is no possibility that we can have this missing energy information because the subprocess center of mass energies are not known. Whereas so therefore, in context of LHC, we only have the missing transverse momentum to be the variable that we can associate with the presence of dark matter in the decay chain or in the production level. Or in context of P plus P minus machines, of course, we can have the missing energy as an additional variable to probe dark matters with. Now, here I have done a very simple exercise that how this missing transverse momentum is this particular variable that is actually related to the x component and y component momentum of the dark matters, right? So suppose we consider a reaction like A plus B going to C plus D plus E, where this so why it is not changing? Yeah, okay. So where D plus E is the dark matter, these are the two dark matter particles. So of course, I mean, in principle, we should define the ET/ or missing transverse momentum as sum over x component momenta of D and squared and sum of the y component momentum of D plus E and squared and taken the square root. Now, the point is, we do not see the dark matters at the collider. So the question is that somehow it reduces to PXC plus PXC square plus PYC square. And that is the visible PT that we have, because C is the particle which is only produced that can be seen in the detector level. And one second. Some problem with the slide changes.
You should click on it.
Yeah, I'm clicking, but it was not responding. The collision occurs along the Z direction. So basically PXC plus PXD plus PXE is equal to 0. That is the mandate because the collision is occurring along the Z direction. So PXD plus PXE is therefore minus PXC, and PYD plus PY is minus PYC. So this is the way then we can actually relate this transverse momentum associated to the dark matters to the visible transverse momentum that is there in the collider. But unfortunately, so far we do not have a sufficient excess in any kind of dark matter signal associated with the missing transverse momentum at LHC. So what this provides a bound on the basically dark matter parameter space. The next point was to look into the other reaction where we look for dark matter is the direct search reaction. Assuming that we are all moving in a dark matter halo, the dark matter can scatter off a detector and then that can provide a nuclear recoil. Now this nuclear recoil rate can be related to this functions of the dark matter density, its velocity distribution, and this rate which is called d sigma DER. Like for example, the velocity distribution is usually this Maxwell distributions, and then this d sigma DER that has essentially two different components. One can come from the spin independent part and one can come from the spin dependent interactions. That also depends on what kind of dark matter model and what kind of interactions that we have. However, once again, then what you do that you actually look for excess in this kind of recoil rates, and unfortunately we have not seen any excess so far, and that once again provides some strong bound on the dark matter models from this null direct search results. So usually people do it like plot in terms of WIMP mass versus WIMP nucleon cross section plane, where you see a bunch of lines, very busy slide, where a very busy plot essentially with all these different dark matter experiments providing a limit of not seeing a dark matter so far in the different experiments. So in a model building analysis, what you do that you find a relic density allowed parameter space of your dark matter model, and then you choose the latest bound, say for example xenon 1 ton, roughly of the order of 10 to the power minus 47 centimeter square, and just you put you abide by the bound, and anything that lies below it is essentially the allowed parameter space of our model, and that can be probed in the future sensitivities of direct search and collider search experiments. And there is one worry which is going on because we are coming close to the neutrino floor where the detection between dark matter and neutrino is going to be very difficult. Okay, now let's come to this dark matter standard model interaction, how we can build this. And this procedure is very simple, that we take an operator which involves both dark matter and standard model particles. And depending on the mass dimension of this operator, we have to basically adjust the total mass dimension by some new physics scale lambda, and that lambda to the power n minus 4, where n is the dimension of this OSMDM that I'm writing. And this operator has to be invariant under the standard model symmetry and the dark sector symmetry and Lorentz transformation, of course. And most often we talk about, like, the dark sector symmetry is Z2, which most often we talk about. There is also a possibility that if we demand that our this operator has two parts like ODM and OSM. It is factorized into ODM and OSM, where ODM consists only dark matter fields and OSM consists only standard model fields. This can only be done when we assume that the dark sector doesn't have a transformation under the standard model, where the standard model fields also do not have a dark transformation under the dark sector symmetry. So this kind of factorization is often that are there, particularly concerning the Higgs portal scenarios that we talk about. All right, so let's come to the simplest dark matter standard model operator, and this is basically the Higgs portal model that we are just trying to elaborate upon. Now, first of all, I mean, if we want to talk about the renormalizable interactions between the dark sector and the standard model sector, then we choose to restrict with n equal to 4. And so therefore, we would like to look upon some OSM of which are standard model gauge invariant. And there are only two OSM operators that we can think of. One is H dagger H and the other is B mu nu, where B is the hypercharged field essentially. And as you can imagine that if you have a mass dimension 2 OSM, the easiest way that you can actually stitch it to a dark matter sector to construct a renormalizable dark matter standard model interaction is to stitch a phi square term with this H dagger H, right? And if phi is a scalar singlet, then phi square is a completely legitimate term. And this is a famous Higgs portal interaction that we all talk about and we all know. However, this doesn't describe the scenario completely, because if you have to, on top of that, demand that phi is a dark matter, then it has to be electromagnetic charge neutral. So anyway, I mean, if it is a standard model singlet, that automatically ensures that it has a zero hypercharge and so zero electromagnetic charge. But we will see some exceptions where we can have extended symmetry, where we go beyond this factorization that I just talked about, and we can also have phi as higher, transforming under standard model field, and we will see those exceptions in a moment. There is another thing on top of this which we have to ensure, which is the stability of the dark matter, which I just talked about, that we have to ensure that phi square is the only term which is present, and that can be ensured by a Z2 symmetry that is demanding that phi goes to minus phi under this transformation, and that gives you only possibility to write is phi square or its higher orders to be Z2 invariant. And in that possibility, the only n equal to 4 interaction that you can write is this h dagger h phi square, which I just talked about. And it also prohibits a term like phi h dagger h, right? So this is important. So therefore, this is the simplest Lagrangian that you can write, and which describes this, what you call the standard generic scalar Higgs portal model, where you have the VH phi describes the Higgs the potential with the Higgs terms, and you have the terms like mu phi square, the interaction, self interaction lambda phi to the power 4, and the portal term that we just talked about. And importantly, when it comes to the dark matter phenomenology, there are only two parameters which controls this whole scenario. One is the mass of the dark matter, and the other is this portal coupling, which we call lambda 1. Okay, so now let's talk about dark matter annihilation and relic density in the present model. So what we have is a phi HH interaction, and after H gets a vacuum expectation value, we also have a phi H term. So these are the possible annihilation terms, annihilation channels that this particular dark matter can possess. So what you do, that you actually compute all the annihilation cross sections for this dark matter to deplete, and then you put it back in your Boltzmann equations and you solve it, or you just put it simply here and you try to find out the correct relic density allowed parameter space of the model. And the relic density allowed parameter space of the model looks like this in terms of this m phi 1 versus lambda 1 parameter space, where this orange line that you see is the correct relic density allowed parameter space. Now, you see here that this the region above is the region where we have underabundance. That means the annihilation of dark matter into standard model is larger than what you require to achieve the correct relic density, and the one below is where the annihilation is smaller than what you require to achieve the correct relic density. And this
So I think his connection might have some connection issue.
Shall I call him?
Yeah, maybe you can call him. Yeah, please. Yeah, please bear with us. Maybe speaker has lost its connection.
hello.
Yes, we can hear you. Please share your screen.
Yes.
I'm really sorry for this trouble. I mean, okay, so let me share the screen once more. Okay, so this is where we were aware. So we were talking about its different.
I think this slide is done. Probably where you are talking about the detection grounds.
Yeah, so let me quickly go through this part. So basically, I wanted to talk about that there is a resonance drop, and this resonance drop is at mH by 2. And this is something which is obvious actually, and it, I don't know this. Yeah, this is obvious because this annihilation channels are proportional to 1 by s minus mh square whole square. So when s is equal to 4 m pi square essentially, then at m pi equal to mh by 2, you enhance the cross section. So therefore you have to drop your coupling so that you get the correct relic density. So now let's talk about the direct search possibilities of this dark matter. So phi can scatter off the dark matter, the detector nucleon via this Higgs portal channel once more. And if you compute this, then the expression comes like alpha n square mu n square by 4 m pi square, where this mu n is the reduced mass and alpha n is essentially the form factors multiplied by mn into lambda I by mh square. And the values of these are actually obtained from different experiments. Now, the important point which I was mentioning, that because we have not seen an excess, the xenon wonton bound of taking sigma SI less than 10 to the power minus 47 centimeter square actually puts a bound on this coupling of the order of 10 to the power minus 3 and so on. The other important point for the Higgs portal models with the dark matter is the following: that whenever the mass of the Higgs is smaller than sorry, I think I had a typo. So whenever mh is greater than m pi by 2, that is m pi is less than mh by 2, then the Higgs can decay to a pair of dark matters, and the decay width can simply be computed. And this contributes to so-called Higgs invisible decays, if you wish. And this invisible decay, these are actually constrained by the experimental searches. This is an old plot. This was actually from E plus E minus to Z. I think it's actually at the Atlas from the ZH production and
Sorry
the
to disturb.
decays.
You have 5 more minutes. Sorry.
Okay, all right. So there is a 95% confidence level exclusion bound on the invisible Higgs branching ratio. And this is less than 0.1 roughly. And this puts a bound like lambda 1 of the same order, like 10 to the power minus 3. And assuming the standard Higgs decay width. And in the high luminosity LHC, you expect the branching ratio to go to probe the invisible branching ratio to even smaller order, so that this exclusion can be even more crucial. Now, let's come to the dark matter production at LHC. Now, Higgs portal models. So basically, you can imagine that the productions of the Higgs channels are essentially the ways to probe the Higgs portal models in context of LHC. So the most important challenges are ZZ, TT bar, and TW, and all associated with the missing transverse momentum. You can also have this monojet or mono X signatures when you have initial state radiations after the Higgs production and its subsequent decays, or upshell Higgs production to phi. But these production cross sections are very, very small, as you can perhaps see here in this particular computations done by Juadi et al. And this brings me to the summary plot of this standard Higgs portal model, where you can see that the region beyond, so this is once again in the m pi versus lambda 1 plane, and you see that the direct search cross section, direct search constraints put a strong limit on the dark matter mass above 100 GeV's order, beyond above the resonance, while below the resonance the strongest constraint comes from these invisible decays. And the direct search constraints once again wins over the constraints that you see from this collider production, which are shown by these blue and green lines on top. Okay, and then there is another possibility that you can have a derivative Higgs portal, and basically you say that del mu phi square del mu h dagger h is a completely legitimate term, and the annihilation channels are the same for this particular case. But because this interaction vertices are momentum dependent, direct search cross section is very, very feeble, and together with this invisible Higgs decay width, you can find this is the allowed parameter space of this kind of a model, and this of course looks better better, at least for the region beyond the Higgs resonance, where because the direct search constraints are absent. Okay, so then there are plethora of possibilities which I thought to talk about, but for the lack of time, I don't have many things to talk about. For example, if you now assume that this phi, the scalar field, is not a real scalar singlet, but a complex scalar and transforming under Z3, then there is a term like phi cube that you can actually write, and that can give rise to something called semi-annihilation possibilities. And the semi-annihilations can also be realized via the Boltzmann equations of this particular form, where on top of the first term, you have a semi-annihilation channel added to it. And then you can see that there is this bulge which is actually coming down from the direct search scanner. And this is basically the semi-annihilation regime where, the annihilations to this H and phi 1 star basically helps you in the depletion of the dark matter density, but evades some of the direct search constraints.
Sorry, possibly again we have lost him. Wait, Professor Bhattacharya, can you call him again?
Okay. Yeah, I think.
Yeah, so it's very unfortunate. My connection was very unstable today. Thanks to my IIT Guwahati office Wi-Fi. So basically, I couldn't cover some of the parts of the discussions, like,
Can you please share your screen? Yeah, your screen has not shared actually. Or if you don't want to.
Yeah, I would like to, but yeah, it's a menace that we are going through. If you give me a couple of minutes, I will try to summarize. Okay, is that all right?
Yeah, it's fine.
Okay, so basically what I tried to say, that if you add two scalars under the same symmetry, then the heavier one actually decays into the lighter one, but there are co-annihilation channels, and that actually provides you a larger breathing space to have more Rayleigh density allowed points beyond the direct search scanner right now. And then you can also have two different dark matters transforming under different symmetries, and that will provide you a dark matter conversion, which you have to add via coupled Boltzmann equations. And in this process, essentially, the heavier dark matter component can convert into the lighter one, and that depletion helps it to evade some of the direct search constraints. Then, of course, instead of assuming that you have a scalar singlet, you can also think of a doublet and still stabilize it by a Z2 symmetry, and this is the famous inner doublet model. And then there are different annihilation channels, and there are larger annihilation and co-annihilations due to gauge coupling, and mostly they are underabundant. However, the Higgs resonance region is still allowed. And for this class of models where you have this doublets, at least providing you the correct dark matter, there actually you can produce these charge components at the collider and subsequent decays, and that gives you this multi-lepton or multi-jet signatures at the collider, and these are more easier channels to probe the dark matter through. So then we can also talk about the fermion singlet, but because I don't have time, so I cannot go through that. Essentially the same thing as about fermion. The only point is that fermion cannot couple to the Higgs portal via a renormalizable term, it has to be suppressed by 1 by lambda, or otherwise you have to incorporate another scalar into the picture. And then once again, the resonance regions are what allows you to evade the direct search bounds. And this is actually a very important plot which I would like to draw your attention towards. If you think of all these possible models of dark matter, scalars, fermions, and vector bosons couplings to the standard model sector via the Higgs portal, then you see that beyond the mh/2 limit, the breathing space is very, very less. I mean, it's almost closed. The sigma, the WIMP nucleon cross section is ruled out to a significant extent for vector, scalar, and for fermions, for all of them. All right, so then you can do other phenomenologies. I think I would like to just go to my summary and conclusion slide. And here is what I had to say, that the Higgs physics provides a natural window for probing dark matter physics via the Higgs portal interactions. However, within the Higgs portal regime, there are different possibilities of dark matter physics, and the difference may show up in direct search or collider search experiments. Usually the direct search sensitivity is much larger than the collider searches, and unless there is an absence of spin-independent direct search reactions, invisible decays of the Higgs almost completely, closes the window beyond mh/2, and Higgs resonance regions are the ones which are still faintly allowed by the direct search. Otherwise, you have to take this, whether it's scalar or this fermion or vector boson, they are allowed of the order of a TeV. And Higgs portal models are difficult to probe at ILC because the Higgs production, excepting for ZH production, there are not many channels by which you can produce them. And there are some other interesting features of Higgs physics which I didn't have the time to talk about. One is the electroweak symmetry breaking, which plays an important boundary to for the dark matter depletion, because they are different before and after. And the second point was vacuum stability, and Rohini had a beautiful discussion today morning. And this vacuum stability condition essentially allows or favors some of the dark matter models over others. And in that sense, scalar dark matter scenarios which are coupling to the standard model Higgs sector via the Higgs portal are more favored than the fermion ones, and so on and so forth. And they can also help you evade the metastability of the standard model Higgs potential. So that's with that, I would like to end the talk. Thank you.
Yeah, thank you very much for the informative and interesting talk. So maybe you can take a single short question.
Yeah, I apologize once again for all the.
No, it's fine. Yeah, it's not your problem. There is no question, it seems. So I maybe ask, can I ask one question? So
Sure, please.
Did you check these things like this simple Higgs portal model, the resonance region with recent LG data? Because around 30 GB, that has a kind of factor 6 or 7 better sensitivity compared to Xenon 1 So whether that would survive with LG or not, do you have any comments regarding that?
No, I haven't checked it. Yeah, so these plots that I all show from, these are the old plots. Yeah, possibly. I mean, the Higgs resonance region is also ruled out by this recent data that I really have not checked. Yeah.
Okay. Yes. Okay. Maybe we can go to the next speaker. Yeah. Thank you very much. Yeah. So our next speaker is Professor Surapna Das, she's from Asuka University. She will talk us about why Higgs inflation. So Professor Das, you can share your screen.
Can you hear me?
Yeah, we can hear you properly.
So let me share my screen.
Yeah, you can see your screen. It's still not in full screen mode. Yeah, it's now in full screen mode. Can you check changing the slides?
What's going? Okay.
Yeah, maybe you can start.
Okay. Hello everybody, and let me thank the organizers of this one-day conference to invite me to talk about Higgs inflation. I would like to start with two disclaimers. First is that I am not an expert on Higgs inflation. I have never written a paper on Higgs inflation. So this is the first disclaimer. And the second disclaimer is whatever I am going to talk about today is not my work because I haven't worked on Higgs inflation. So the organizers had only asked me to give you an overview of what Higgs inflation is, and that is what I am going to do. That is my job today. So in next 20 minutes, I'm going to, or 25 minutes, I'm going to talk about why we required Higgs inflation at the first place. And I presume that this is the only talk on inflation in this whole cosmology. So I would like to give you a lot of cosmological aspects. First of all, I'll spend some time to build up the problem why we needed inflation at the first place, Higgs inflation at the first place. And then I'll, at the very end, I'll tell you how Higgs inflation solved those problems in inflationary cosmology. So by saying that, let me start with some cosmology. So maybe you have seen this picture many a time. This is how, according to the Big Bang, our universe has evolved.
Sorry, your screen is not changing probably.
It's not changing?
No.
Or me it is changing. You cannot see the next slide?
No. We are in the first slide itself by Higgs inflation.
Oh, okay.
Maybe you can reshare, I don't know.
Now can you see?
No, maybe you can reshare it. I mean, stop
Okay.
sharing it. Okay.
Can you share see now?
Yeah, we can see it now, but it's not in full screen mode. Can you please change it right now? Maybe you can check that. Change the slide.
Can you see some?
No, it's not changing actually.
Can you see the next slide?
No, we cannot.
Okay.
Can you stop share and again reshare maybe?
Stop sharing. So let me see. Okay, so let me share again.
I can see.
Can you see this?
Yeah, we can see the first
Now,
slide.
second slide?
It is changing right now. Yeah.
Okay, good. So very good. So I hope you have seen this picture many a times because I mean, this picture tells you how our universe has evolved from Big Bang to the present state. And at the very early stages, we have something called inflation, during which the universe expanded exponentially. So it was a very rapid expansion through which our universe probably has gone through. We don't know yet, but we have strong evidence that this might be true. So inflation was something which is very at par with the observations right now. So, and we needed inflation because there were some pathologies with the Big Bang theory, which inflation solves. I don't have time to go through that, but this is an era which has been added by hand. So to start with, Big Bang cosmology did not had inflation. It was added by hand in 1980s because there were some pathologies, as I said, in Big Bang theory, and inflation was required to solve those pathologies. So after the exponential expansion, the universe enters a radiation dominated era. And during this era, the universe was expanding, but at the same time, the expansion was decelerating as well. Radiation dominated because the particles inside the universe the temperature of the universe was very high, and all the particles were relativistic in nature. So basically, we treat them relativistically, and that's why we call this as a radiation dominated era. But as the time goes, the universe expands and the temperature goes down. So the particles started to become non-relativistic, and when they become non-relativistic, we enter a matter-dominated era. And during the matter-dominated era also, the universe expands, but it expands with a decelerating rate. and the universe we treated non-relativistically during this era. Something very important happened. Can you see my slides?
Yes, yes,
Okay.
you are in the second slide.
Okay. So, okay. So during during matter domination era, something very important happened. That is the formation of the cosmic microwave background. The photons, which were very tightly coupled with the matter of the universe previously, it got decoupled from the rest of the matter, and it started free streaming us towards today. And this is the photons that we see today in the microwave range. And this is a very important discovery. And because before the formation of CMB, the universe was opaque to us. We could not see anything from that part of the universe because the photons were very tightly coupled and the mean free path was very small. But when the photons decoupled from the rest of the universe, of the rest of the matter of the universe, it started to free streaming towards us, and we can actually detect those photon today. And whatever imprints that were imprinted on these photons can be analyzed, and we can actually predict what had happened before the CMBR were decoupled. So formation of CMBR was one of the very major epoch, a major event in cosmology. And it was discovered in 1965. So Penzias and Wilson had discovered the CMB. They saw a very uniform temperature of photons coming through all over the sky. In 1992, the Kobe experiment was sent, the Kobe satellite was sent, and it measures that the temperature is not very uniform, but it has fluctuations all over the sky. And it has actually two, there are some hot spots and there are some cold spots. And these temperature fluctuations are of the order of 10 to the power minus 5 Kelvin. So if the uniform temperature is 2.73 Kelvin, this temperature fluctuations are of the order of 10 to the power minus 5 Kelvin. And in 2003, WMAP was sent, and it has measured the temperature fluctuations in a more precise way. So you can see how the CMB sky has evolved since 1965. So we know our CMB sky very precisely nowadays. And Planck has even measured the sky in a more precise way. So this was Kobe, this is WMAP, and this is Planck. So we know the CMB sky very well. So what are the informations? Not only the CMB photons have temperature fluctuations, the CMB photons are also polarized. So it can have two kinds of polarization, E mode and B mode. I don't have enough time to go into those details of how these polarizations were generated in the CMB photon at the first place. But this for the polarization of photons actually contains a lot of information about what might have happened during inflation. I'm going to tell you about that. So this is the uniform temperature which fits the black body spectrum very nicely. So the temperature is 2.73 Kelvin. And this is the 2-2 correlation function of the temperature fluctuations, which is the 10 to the power minus fluctuations that Kobe first saw. And this is the plot from Planck observation. So this is the 2-2 correlation function of the temperature fluctuations of the CMB photons. And you can see that these small blue dots, it came with the error bars. So how precise this 2-2 correlation have been measured by the Planck, you can see. And this red line, which fits this data, is a prediction from inflation. So inflation predicted that if there is a CMB photon, I'm going to elaborate on that. If there is a CMB photon, there has to be temperature fluctuations on the CMB photon, and this should be the correlation function. So this is a precise prediction from inflation, and that's why we believe that something like inflation might have happened at some point of time at the very early ages of the universe. So as I said, we don't have not only temperature fluctuations, but we have polarizations like E polarizations and B polarizations. They can also be measured by their 2-point correlation function. So this is the TT spectrum, then there is a TE spectrum, then there is the EE spectrum. There is no TB spectrum because of polarity violation. So, but there is a BB spectrum. This TT spectrum is sourced by something called scalar perturbation, which was generated during inflation. And then there is this BB spectrum, which is sourced by the tensor perturbations, which are generated during inflation. I'm going to elaborate on that. And these two spectrums are very important. TT spectrum we have observed, but the BB spectrum are yet to be observed. We have upper bounds on the BB spectrum, but we have not yet measured the BB spectrum. Okay. Then, what is the theory behind it? Theory is, of course, Einstein's general theory of relativity. And inflation, as I said, it is a very brief epoch of the early universe when the universe expanded exponentially. And the dynamics is given by the Einstein's field equation. On the left hand side, we have this something called G mu nu, which tells us how the background space-time universe of the universe evolves. And T mu nu on the right hand side tells us how the matter evolves. So the geometry and the matter are coupled, and the moment we change the matter content of the universe, the space-time starts to evolve differently, and vice versa. If you change the metric, then so basically what Einstein's equation tells us is that the matter and the geometry are coupled with each other. So during inflation, this G mu nu or the background metric is given by what is called the Friedman-Robertson-Walker metric. So this is just like a Minkowski metric that we are very familiar with. The only exception is that before the spatial part, there is a scale factor sitting in front of it. So this scale factor, as you can see, that it is a function of time. So it says that the space-time is expanding. Okay. And during inflation, this expansion is exponential. So the scale factor is an exponential factor of time. And this H is called the Hubble parameter. So you need some matter to make the universe expand exponentially. What kind of a matter can make the universe expand exponentially? That requires a slowly rolling scalar field, which is called as an inflaton field. And for the slow roll of the scalar field or the inflaton field, we require the potential of the scalar field to be very flat. So the potential actually plays a very important role, and it's going to play a very important role in my talk as well. So the shape of the potential in inflationary theory is a very important aspect. Unless and until it is very flat, the slow roll will not occur, and it will not make the universe expand exponentially during inflation. So the shape of the potential is going to play a very important role. Just keep it in mind. And the slope of the scalar field is measured by the slow roll parameter epsilon and eta. Epsilon is proportional to the first derivative. So prime is del v by del phi, and double prime is of course del 2 v by del phi 2. So these are the measure of the slope of the inflaton potential. Okay. So this is the simplest picture of inflation. And as I said that we require a scalar field to have inflation, but this scalar field is actually a quantum field. So it has a background classical field like a wave, and then there are quantum fluctuations around it. These quantum fluctuations, then because the matter and the geometry are coupled, if there are perturbations on the matter part, there are perturbations on the geometry part as well. Then that matter part in the geometry will give you perturbations in the capital G mu nu or in the Einstein tensor. So on the right hand side, we have only a scalar field. So if you perturb the right hand side, we get the perturbations in the scalar field. But on the left hand side, we have a metric G mu nu, which is a tensor, rank 2 tensor. And when you perturb a rank 2 tensor, you will get all kinds of fluctuations, scalar perturbations, vector perturbations, and tensor perturbations. Vector perturbations do not play a bigger role in inflation because they decay during inflation very fast. So we don't bother about the vector perturbations, but the scalar perturbations and tensor perturbations are of play a very important role. Scalar perturbations give rise to the TT correlation function or temperature correlation function in the CMB sky, and the tensor perturbations gives you the BB mode correlation function because the tensor perturbation sources the B mode of the CMB photons. So this play a very important role. So this is how the scalar perturbations in the metric look like. So the scalar inflaton field has a perturbations delta phi, and the metric has this curly phi as its perturbation. And we study both these perturbations as one perturbation, which is known as the co-moving curvature perturbation. And during inflation, what happens to this perturbation? First of all, this perturbation has a length. Length I am denoting is as lambda. During inflation, this is like a de Sitter expansion. So the horizon remains constant and all the length scales are expanded because of the expansion factor. And the expansion factor during inflation is exponential. So any length scale which was initially sub-horizon will soon become super horizon because of this exponential expansion. So it was before, if it was inside this horizon R, and then it was expanded beyond R. So this become super horizon. And this curly R, or whatever I have denoted here as a co-moving curvature perturbation, this perturbation freezes on super horizon scale. That means they don't have any dynamics. So it is good. We know only in the sub-Hubble region that the physics is causal. So when the physics is causal, we evolve this co-moving curvature perturbations and let them go to the sub-horizon scale where they freezes. And then again, they re-entered the scale, the Hubble radius during the matter-dominated era or the radiation-dominated era. When they enter during the matter-dominated era, they perturb the radiation part. And when they enter during the matter-dominated era, they perturb the radiation matter part. The radiation perturbation gives rise to these temperature fluctuations in the CMB sky, and the matter perturbations later on gives rise to the galaxies. They grow as galaxies. So these temperature fluctuations, now you can understand that it has been sourced by the inflation. So this 2-point correlation function, so this scalar perturbations which were generated during inflation are actually related to the temperature fluctuations on the CMB sky. So when we calculate the 2-point correlation function of the scalar perturbations during inflation, which is known as the power spectrum, this power spectrum which was generated during inflation gives rise to the 2 correlation function of the CMB sky that we observe today. So this is how the predictions of inflation is being tested in the CMB sky. Okay. And the tensor perturbations has a similar property. So this is the tensor perturbation part, Hij. And it has 2 polarization state like any gravitational waves, plus polarization and cross polarization. Each helicity acts like a massless scalar in the de Sitter space. So the analysis is just like the scalar perturbation that we discussed just now. Only you treat these 2 polarizations separately and then you sum up at the end. So what is the prediction of single field inflation? As I said, the scalar, this is a scalar power spectrum, 2 scalar power, 2-point correlation function of the scalar fluctuations. And it has a scalar amplitude and some scale dependence. How much it will depend on the mode number. Okay. And the observation, the prediction of single field inflation is that the scale dependence, this NS, is actually proportional to the slow roll parameters. And the slow roll parameters are very small because the slope of the potential has to be very, very small. So the NS deviates from 1 very less. So the observed value of the spectral index is 0.96. So you can understand that it is almost equal to 1. That only because this NS minus 1 is proportional to the slow roll parameters. So this is the prediction and this has been observed. So you can understand that the predictions of the inflationary theory is actually being tested in the CMB sky. Then inflation produces the correct amplitude of the power spectrum. As I said that the temperature fluctuation in the CMB sky is of the order of 10 to the power minus 5 Kelvin. And when you measure the 2-point correlation function, they become 10 to the power minus 10. And inflation produces a scalar amplitude which is of the order of 10 to the power minus 9. So they are all consistent. So the inflation tells that there has to be temperature fluctuations of the order of 10 to the power minus 5. Okay. Then there is the tensor power spectrum again. So this has not been measured. As I said that the BB power spectrum has not been observed yet. These are just the predictions so far. So what is the prediction? One is that NT has to be again small. It is a red tilted. It is also proportional to the slow roll parameter. And what is the most interested quantity is how much tensor is generated with respect to the scalar power spectrum. So R is a very important parameter, and this is the prediction of the inflation is that also should be of the order of the slow roll parameter, that should be very less. And the observational bound today on R has to be less than 0.064. Okay, so just remember that the tensor to scalar ratio has to be smaller than 0.064. Now, knowing the scalar perturbation and tensor perturbations, and as I said, this red curve is the simplest. You take the simplest single field model of inflation, just slow roll, canonical kinetic term, and this curve is being fitted very well. There's no problem with that. But then you can go beyond a single field inflation and create many inflationary models, because there is only two parameters to fit, AS and NS. There can be many. So this is a non-exhaustive list of inflationary models that exist today. So you can see there how many variants of inflationary theory then one can play around with. But the important part is what should be the potential. And when you ask what kind of potential inflaton can have, you can also ask where you can put this inflaton field in our particle physics model. Can our particle physics model accommodate this inflaton field? And we have only standard field, the standard model particle physics, and there is only one scalar field, which is the Higgs field. So the question then remains whether a Higgs field with its Higgs potential can run inflation during the early universe. Now the question is, so what is the potential of the inflaton field? So this is a plot from Planck, and this is, so on the x-axis there is the scalar spectral index nx, and on the y-axis we have the tensor to scalar ratio r, and you can see that lambda, if we have the quadratic potential, m square phi square kind of potential, this is this black line, and this is already quite ruled out by the observational aspect. And lambda phi 4 is not even in the picture. It is just out of the picture. It is actually ruled out. Why it is ruled out, I'm just going to tell you about that. But you can see that this R square inflation is this, and this is R square inflation is actually Higgs inflation, but Higgs inflation matches with the observation very well. So Higgs inflation predicts.
Sorry, you have 5 more minutes.
Okay, yes, I'll try to wrap up.
Okay, thanks.
So what is the problem? The problem with, so we want a lambda phi 4 kind of potential, because Higgs potential is it does look like phi 4 potential. So what is the problem with phi 4 potential? Why it is not there in this picture at all? Because the problem is twofold. The problem is, first of all, you see that this is the scalar amplitude, and it is proportional to the potential of the scalar field. If you calculate if you take the potential as lambda phi 4, then you can see that the scalar perturbation turns out to be proportional to lambda. And if you want the scalar amplitude, perturbation amplitude of the order of -9, which has been observed, lambda has to be fine-tuned of the order of 10 to the power -13. So this cannot be the Higgs field, because we know for the Higgs field, if there is a lambda phi 4 kind of a potential, then lambda is of the order of 0.01 or 0.1. So it cannot be the Higgs field, because lambda has to be very fine-tuned so that you can actually have the observed scalar amplitude. Okay. And also, if you just take lambda phi 4 kind of potential, it gives rise to a very large tensor to scalar ratio, 0.2, where the upper bound is 0.06. So these are the two kinds of problem lambda phi 4 potential faces, and that's why from this plot we can see there is no lambda phi 4. It is ruled out. Okay. So Higgs scalar in large field limit, we know it looks like a lambda phi 4 potential. So Higgs scalar cannot play a role of inflaton, because it is now ruled out. Lambda phi 4 potential cannot play a valid inflationary potential, as I have just explained. But how to make it a valid inflaton potential? That is the work done by Bezrukov and Shaposhnikov in the year 2008. And I just checked the citation of this paper only yesterday, and it had a citation of 1747. So you can understand that this paper is very famous. So the whole problem is to make lambda 5/4 potential a valid inflaton potential, so that standard model Higgs boson can play a role of inflaton. Okay, so this is to get away with the problem. What this Shaposhnikov and Bezrukov propose, that you have your Higgs field. So this is the kinetic term of the Higgs field. This is the potential term of the Higgs field. But now you couple your Higgs field with gravity. So this is the R is the Ricci scalar, and you couple this Higgs field with your gravity. Now this is called so this kind of a thing is very difficult to analyze. So what one does is that one goes to the Einstein frame by rescaling the G mu nu part, and where this is called the conformal transformations. The conformal transformations here, omega square is just this factor 1 plus chi h square by m Planck square. And once you rescale your metric, you go to a frame where the gravity looks that you get rid of the non-minimum coupling of the scalar field with the gravity. You just have the Einstein gravity here, and your matter gets decoupled from the gravity. So this chi and h are some redefinition of the field. And the lovely thing is that you get a potential which does not look like a 5/4 potential in this Einstein frame, but it is a very flat potential. You can see this is 1 plus exponential of some factor, and when the on super Planckian scales where chi is much greater than m Planck, this exponential factor is basically 0. So this gives you a very flat potential, not like a lambda 5/4 potential in the Einstein frame. So you get a very flat potential in the Einstein frame, and that solves the problem. So this is the prediction of Higgs inflation. So you have now you calculate your number of E4s that is required, and your scalar spectral index and tensor to scalar ratio. Everything can be written in terms of your number of E4s. So in Higgs inflation, NS turns out to be correct order of whatever has been seen, and R turns out to be 10 to the minus 3. So you remember R has a upper bound of 0.06, and this is lower than the what has been observed. So that is why this Higgs inflation, this one, is sitting at the sweet spot of the R versus NS plot. So this is the WMAP plot, but it also sits in the sweet spot of Planck observation. And how you can claim that this is a Higgs inflation, and so that your lambda can be of the order of 0.01 or 0.1 to make your AS 10 to the power minus 9, you have to have your non-minimal coupling with the gravity very high. So only when your zeta parameter is 10 to the power 4, only then, if you have a very strong non-minimal coupling of the Higgs field with the gravity, only then you can make your lambda to be of the order of 0.1 and make your Higgs field to become an inflaton field. So just let me sum up. So this is how Higgs inflation solves the problem. So let me sum up. So Higgs inflation mechanism makes the mechanism of Higgs inflation is to try to make quartic self-coupling potential a valid inflationary potential. And the quartic self-coupling now need not have to be very fine-tuned. It can be of the order of 0.1, but at the cost of a very high non-minimal coupling with the gravity. The tensor to scalar ratio also reduced and becomes well below the observational bound. So this model is very valid with the observational bound. But the drawback is that you have to have a very huge non-minimal coupling with gravity, which is unavoidable. And this is also known as the unitarity problem of Higgs inflation, and people have worked on this problem for a very long time. I don't think there is a very sound explanation to it, but anyway, so this is Higgs inflation. Thank you.
Yeah, thank you very much for the nice talk. So if you have a quick short question, maybe you can address that. Seems that there is nothing. So is there any way to probe? So can I ask a question?
Yeah, sure.
Is there any way to prove this large coupling with this graviton and Higgs? I mean, is there any experimental way to prove it?
In colliders?
No, not colliders. I mean, anything in any
No,
experiment.
even in
ground and-
cosmology, we don't know whether there is a large minimal coupling or not. There's no way to probe it. Only this scenario works. That's
Okay.
why. So that's true.
Okay, maybe we can close the session here and thank you everyone. Thank you each of the speaker for presenting. And we'll meet at maybe 4:25 for the next session. Professor Bhattacharya, is this fine? We meet at 4:25.
Make it 5 minutes break. Let's
Sorry.
meet at 4:20.
Sorry, I cannot hear you. Professor.
Let's meet in 5 minutes.
Oh, okay.
Okay. 4:20 then, right?
Okay.
Okay.
We start.
Should I start?
Yeah, you should.
Okay. Is Professor Manimala Mitra is here?
Yeah, I'm online.
Okay. Welcome to the last session of this virtual meeting. Okay, so in this session we have 3 talks. 2 of the talks of half an hour and last talk will be of 45 minutes. So the first talk in this section will be given by Professor Manimala Mitra. She'll be talking about a probe of seesaw with Higgs. Please, could you please share your screen?
Yeah. So I will switch off my video.
Yeah, that is okay.
Yeah.
I think this is Tarak's
Yeah,
screen.
I think someone has to stop sharing. Yeah.
Is this visible?
Yeah, this is visible. Yeah, your screen is visible. Can you just try to change your slides so that like we can see it's working?
And is this full screen mode or no? No,
It's not.
this is not yet.
Yeah.
Full screen. Okay.
Yes, now it's in full screen.
This was right.
Yeah, slides are changing.
Okay.
Yeah, you can start, please.
Okay. So just a heads up. There may be some power cut and then there may be some disruption. Yeah. So because I'm attending the meeting from my home.
Okay, and also I'll inform you after like 5 minutes before your like 10. Okay.
Yeah, that's fine. Okay. So hello everyone. It's a very enjoyable meeting that our colleagues actually have organized, and I would like to thank the organizer for the invitation and organizing such a one-day symposium, which was much required. So I'm going to discuss about seesaw and how we can probe the seesaw with some of the distinctive Higgs signature, hence the talk title, Probe of Seesaw with Higgs. And in my talk, there will be 2 segments. So in the first segment, it will mostly, I'm going to discuss about some of the very, very popular models, such as type 1, type 2, type 3 seesaw, inverse seesaw, and 2 of the gauge extensions, the -L gauge model and retret symmetry. And in the second part of my talk, I'm going to entirely focus on some of the distinctive Higgs signatures that these different models can actually accommodate. So although I'm going to focus more on the collider searches, but there will be 1 or 2 slides where I'm also going to discuss about few of the non-collider searches. So what we know, all of us know that neutrinos have electron volt mass and they have very specific mixings. And these are the informations that we have at the moment from oscillation experiments, that 2 of the mass square differences are around 10 to the power -5 electron volt square and 10 to the power -3 electron volt square. And there are 3 mixing angles. 2 of them are large, around 34 degree, 47 degree, and the third one is around 8 degree. So this is small but non-zero. Other than these oscillation experiments, we also have some information from the non-oscillation experiments. For example, cosmology. So cosmology gives bound on the sum of the light neutrino masses, which is essentially less than fraction of an electron volt. And we have at the moment relaxed bound from beta decay experiments. So this mu, this beta decay observable is less than 1.1 electron volt, and this was given by Catherine. Now, one of the most profound mechanism to explain this electron volt small neutrino masses is seesaw, where the answer is that the Majorana mass of the standard model neutrino is generated from higher dimensional operator via electroweak symmetry breaking. So the operator that is responsible for neutrino mass generation in this seesaw answers is this dimension 5 LLHH operator, where L is the lepton doublet and H is the Higgs doublet. And this operator is violates the -L by 2 units. And this generates the Majorana mass of the light neutrinos via electroweak symmetry breaking. So light neutrino mass is basically proportional to this U power square, the wave square, divided by the cutoff scale of this effective field theory. And this is essentially the Lepton number violating scale. So the small neutrino mass is inversely proportional to this heavy cutoff scale, which is denoted as M. Now this operator, because it's a dimension 5 operator, so there has to be some UV completed model from which this operator is actually getting generated. And if one unfolds this operator, then at tree level, there are 3 possibilities. So the first one is denoted as type 1 seesaw, and this is the most simplest, where on the top of standard model fields, one adds standard model gauge singlet neutrino. For type 2 and type 3 seesaw, on the top of standard model fields, one adds SU2 triplet Higgs field with hypercharge 2. And for type 3, this is a SU2 triplet Higgs field with hypercharge 0. Now, for the type 1 seesaw, because this right-handed neutrino or the standard model gauge singlet field is a gauge singlet, so therefore it does not directly interact with the standard model gauge bosons. Rather, it interacts with the standard model gauge fields via a parameter which is known as active sterile neutrino mixing. So this is the mixing between the light neutrino and the right-handed neutrino. And this is nothing but basically the Dirac mass divided by the Majorana mass. Now, very strong constraint exists on this parameter, this active sterile neutrino mixing, from light neutrino, electron volt light neutrino mass constraint. So typically, if one asks the question that whether for type 1 seesaw this right-handed neutrino can actually be copiously produced at collider or not, the answer is very pessimistic. So obeying seesaw condition, the production cross-section of this right-handed neutrino is heavily suppressed. Now for the other kind of seesaw, such as type 2 seesaw and type 3 seesaw, because these are SU2 triplet fields, so they directly interact with the standard model gauge degrees of freedom. So they can be pair produced at different type of colliders. Now, this other than this type 1, type 2, type 3 seesaw, there are other variation of seesaw. So for example, this inverse seesaw, and the idea is very much different as compared to type 1 seesaw. Now for type 1 seesaw, this right-handed neutrino, this was a standard model gauge singlet, and it has a very heavy mass. And this was a Lepton number violating mass term one can write in this model. But for inverse seesaw, contrary to that, the Lepton number violating parameter, which is denoted as mu, is extremely tiny. And as mu tends to 0, there is Lepton number asymmetry at the tree level in this theory. So in this model, the light neutrino mass is proportional to this parameter mu and times this Dirac mass and this parameter m whole square. So this will be a whole square. So the smallness of light neutrino mass is basically taken care by a small mu, and therefore this mg by m, this parameter can actually be large. And in this model, there are quasi-degenerate neutrinos, and the active sterile neutrino mixing is basically mg by m. So therefore, this active sterile neutrino mixing, contrary to type 1 seesaw, can actually be quite large. And therefore, in inverse seesaw, in the context of inverse seesaw, these right-handed neutrinos can also have large production cross-section at different colliders. Now, other than these different kind of models, there are various other proposals. So for example, alternative violating supersymmetry. Then there are proposals to generate light neutrino mass via loop. Then there is a very, very interesting proposal by Babu et al. And that the main aspect is that main important point is that suppose dimension 5 operator is suppressed or does not generate at tree level, rather dimension 7 operator generates at tree level. So whether these can give rise to Majorana mass of the light neutrinos or not. So I'm not going to discuss this. Rather, what I'm going to focus on the gauged B minus L model. So this is one of the most simplest extension, gauge extension, where this is U1 B minus L has been added as an extra additional gauge symmetry. And the particle contents of this model is, other than standard model fields, there are 3 right-handed neutrinos for anomaly cancellation. Then there are BSM, Higgs, S, and because of this gauge symmetry, there is additional beyond standard model gauge boson, which is denoted as Z prime. So salient feature of this model is this S, the BSM Higgs, acquires vacuum expectation value and breaks B minus L gauge symmetry. And the Majorana mass of the right-handed neutrino is actually proportional to this B minus L breaking vacuum expectation value. Not only that, the mixing between standard model Higgs and the beyond standard model Higgs also depends on the same wave, this B minus L breaking vacuum expectation value. And the beyond standard model gauge boson mass, this which is denoted as mz prime, this is also proportional to this VBL, which is the B minus L breaking vacuum expectation value. Now, type 1, type 2 seesaw and also this gauge B minus L model, they can nicely be embedded in left-right symmetric theory. And here the gauge sector is SU2, other than SU3C, there is SU2L, there is SU2R, U1B minus L. So this model can actually explain that starting from a parity symmetric theory, how parity violating standard model can actually be achieved. So that is the beauty of this model. Now, at least the version that I'm going to discuss. So there are different variations of left-right symmetric theory, but the one that I'm going to discuss, there are 2 Higgs triplet. So delta L, this is a SU2L triplet, and there is delta R, which is SU2R triplet. Both of them has 2 units of B minus L charge. And this vacuum expectation value of delta R breaks SU2R cross E1B minus L to E1Y. The other interesting aspect of this model is that the right-handed neutrino that becomes a part of this gauge multiplet, and this is completely by the requirement for the sake of gauge symmetry. There are a number of particles present in this model. So for example, right-handed neutrino, right-handed gauge boson, there are Z prime gauge boson, and there is a very enriched Higgs sector. So one of them is this doubly charged Higgs that I'm going to discuss, phenomenology of which I'm going to discuss in detail. So in the next segment of my talk, I'm rather going to focus on the collider signatures, and I will focus more on those models which has a rich Higgs sector. So I will start with Higgs triplet model. So this is a model where this delta plus, the singly charged Higgs is present, a doubly charged Higgs is present, and delta 0 electromagnetic charge neutral Higgs is present. Now these delta interacts with 2 lepton doublet. It also interacts with the standard model Higgs field through this parameter mu delta. And delta 0 vacuum expectation value generates light neutrino mass. So light neutrino mass mu, this is a mass matrix, 3 cross 3 light neutrino mass matrix, is proportional to Y delta and times V delta, where this V delta is actually proportional to this parameter mu delta. So the bottom line is that if mu delta is 0, so suppose this interaction does not exist, then V delta is 0. And if V delta is 0, then the light neutrino mass is 0. So it's not only this. Is there any question? Okay.
No.
Okay. So not only this Y delta is important for the neutrino mass generation, rather Y delta together with this parameter mu delta are important. And together they break lepton number, they are responsible for lepton number violation in this model. The other interesting aspect of this model is that it's extremely simple, because if you look into this U power coupling Y delta, this is completely determined by the PMNS mixing matrix and these light neutrino masses. And of course, this V delta is also there. So once someone gives you this, experimentally, we know this PMNS mixing matrix and we know the mass splitting. So to a large extent, this Y nu is also sort of like known. And a large Y delta is, as we will see, is also responsible for lepton flavor violation. Now, okay, I cannot actually change my slides.
Maybe you can click
Yeah, okay. Now
again.
this is
Again, make it.
working, right?
Yeah, this
Yeah.
is working. Maybe you can try again making it full screen.
Yeah. Sure. Okay. So these doubly charged ticks, other than the doubly charged ticks, this model has few other Higgses. There are singly charged ticks, as I have discussed before. But other than that, there is CP even BSM Higgs H20 and CP odd BSM Higgs, this A0 and H10 is the standard model Higgs. Now, because of these coupling, LL delta, this doubly charged Higgs actually can directly decay into two same sign lepton. This is a this can give rise to very clean signal, but it can also decay to same sign W gauge boson. Now, this decay mode, the partial decay mode of this is inversely proportional to this triplet wave square. Rather, and this H plus plus going to W plus is actually proportional to V delta square. So there is a competition depending on the value of V delta. There is a competition that which decay mode will actually win. So here along in this plot, along the y-axis is the branching ratio of the W charged Higgs, and along the x-axis is the triplet wave. And as we can see that if V delta is less than 10 to the power minus 4 GeV, then the doubly charged Higgs decaying into two same sign dielectron is 100%. And if the doubly charged, if the V delta is more than 10 to the power minus 4 GeV, then the decay into W plus is 100%. So here, of course, we have assumed that the doubly charged Higgs mass is the lowest one among all these different BSM Higgses. Now, for the singly charged Higgs, this is even more interesting. So few different decay modes are possible. So if the triplet wave is less than 10 to the power minus 7 GeV, then singly charged Higgs can decay to lepton neutrino. If it's more than 0.1 GeV, it can fully decay to either WZ, W Higgs, or top bottom. And in the intermediate range, depending on the mass splitting between doubly charged Higgs and the singly charged Higgs, it's possible that the singly charged Higgs will have a cascade decay. By cascade decay, what I mean that it will decay to a doubly charged Higgs and an off-shell W gauge boson. Now, in this plot, actually, it sort of like gives a summary of the different existing constraints. So this is the triplet wave versus mass of the doubly charged Higgs plane. So CMS has looked into this channel, proton going to H plus plus, H minus minus, and each of the H plus plus decays to two same sign dilepton. So at the end of the day, we have 4 leptonic final states, and this is a very clean signal. One can fully reconstruct this H double plus if it's an electron or a muon. And up to 870 GeV has been excluded by Atlas, assuming 100% branching ratio. So this line is, I think it was a CMS line, and it's slightly older, but nevertheless, this corresponds to this search. Now, other than this search, there is this the search from Atlas for this channel, where in the final state we have 4 W gauge boson, and then we can have different multi-lepton final states. So between 200 to 350 GeV has been excluded by Atlas collaboration. But the interesting part is that this search is actually only valid if V triplet is more than 10 to the power minus 4 GeV, and this is only valid if V triplet is less than 10 to the power minus 4 GeV. So as far as the two searches are concerned, there are complementarity between them. Now, for a very lighter doubly charged Higgs mass, so if the doubly charged Higgs actually lower than 200 GeV, a very interesting signature is possible to accommodate, which is that one of the W gauge boson will actually be off shell and it can have displaced decays. So this part is largely unconstrained. And as we go towards higher mass range and larger wave, so this all Hopite region is actually unconstrained. So the intermediate triplet wave range, where it starts from 10 to the power minus 5 GeV to, let's say, 10 to the power minus 1 GeV. So we have looked into possible signatures that may be accommodated for this triplet wave range. And we looked into the cascade decay of the singly charged Higgs. So this is the H plus plus H minus. This is associated production. And then H minus in this intermediate range can decay to off shell W and H minus minus. And at the end of the day, one can have 5W, and from this 5W, we can have 5 lepton plus missing energy, or we can have 4 lepton plus twice jet plus missing energy. So this is sort of like the kind of cross section that is possible to obtain for 13 TeV, 14 TeV center of mass energy, and also 100 TeV. So this is the Atlas exclusion line. So remember, now this is for 4W final states that will give basically 4 lepton. And for doubly charged Higgs mass around this 350 GeV onwards, the cross section is around few femtobarn. But if one looks for 100 TeV center of mass energy, then the cross section is really, really high. It can actually reach up to few hundred femtobarn. And here also you can compare compared to this plot. So this is again few femtobarn, and this is I think few tens of femtobarn. By the way, so this cascade decay, this H double plus going to H plus W star. So this is the other cascade decay where doubly charged, singly charged Higgs is the lightest. That has been looked by long back by Rohini et al. For another proposal, a gamma gamma condition. Now this model, because it has these neutral Higgses, can give another very distinctive signature, which is same sign tetralepton signature. So the charged Higgs can be produced in association with a neutral Higgs, or it can be actually produced H0, A0 final state is also possible to obtain. And then what happens, there are a number of cascade decay is possible. So either singly charged Higgs can decay to a doubly charged Higgs, or H0, A0 can also decay to a singly charged Higgs. And then the singly charged Higgs can decay to doubly charged Higgs. So bottom line is that at the end, we can have 4 same sign tetralepton signature, which would be a very, very clean signal. Now, unlike this, the other production mode, the proton-proton going to H plus plus H minus minus, these final state actually crucially depends on the mass splitting between doubly charged Higgs and the singly charged Higgs, which in turn depends on the quartic coupling of the potential. So by looking into this signal, it's possible to probe one of the quartic coupling, which is denoted as lambda 4 of the potential. So this is the, I think I'm going to discuss this slide. So this we have considered in this work, and because in this production process, a number of branching ratios is involved. So here what we have done in the lambda 4, the relevant quartic coupling V delta plane, we have plotted the overall branching ratio. So the branching ratio, because it involves a number of W going to leptonic decay mode and so on, and also the cascade decay. So the branching ratio is around 0.4%. And what we see that nevertheless, in this lambda 4 V delta plane in this range, okay, so for 14 TeV center of mass energy, and for high luminosity option, around 200 events is possible to obtain. If the doubly charged Higgs or this H0, A0 are very heavy, so let's say 800 and 900 GeV, then this 14 TeV LHC cannot probe that kind of a mass via this signature. So we looked into for a center of mass energy of 100 TeV. And as we can see that here what happens that the lambda 4 in the lambda 4 V delta plane, so this signal is possible to obtain only in a very selective region. So here, not only this W plus channel of the W charged Higgs contribute, but also H plus plus going to L plus also contributes. And this is a summary that if V delta is around between 10 to the power minus 4 to 10 to the power minus 5, and lambda 4 varies between 0.2 to 0.3, then 1000 number of events, so of the order of 3000 is possible to obtain with full luminosity. So the bottom line is specific intermediate triplet wave and quartic coupling can actually be probed with this kind of a center of mass energy. Now, a doubly
Sorry,
charged.
sorry to interrupt. You have 5 more minutes.
Okay. So doubly charged states can also be produced in at E plus E minus collider. So this is typically the kind of cross section that one will achieve with center of mass energy 380 GeV and 3 TeV. So I think I will skip this slide, but the most importantly, if the doubly charged Higgs mass is very heavy, then the produced W plus actually will be very boosted. And rather than a result analysis, a fat jet analysis will be useful. So here what happens that because this doubly charged Higgs, the PT is actually very large, this each of the W is boosted and the final states are super collimated. So we looked into 4 fat jet final states for E plus E minus collider, and the summary is 800 GeV to 1.120 TeV doubly charged Higgs mass is possible to discover with only less than 100 inverse femtobarn of luminosity. Now, the other mass range where doubly charged Higgs has a very low mass, so less than, let's say, 200 GeV. For that, you won't get a boosted W gauge boson. Rather, all the final states will actually be dissolved. So there we looked into multi-jet final states. So we demanded more than equal to 7J. And what we see that this kind of mass range, so between 137 to 172, can actually be probed with luminosity less than 100 inverse 1. The other interesting proposal that I actually very recently came across is probing this quartic coupling, this lambda fold, via another signal, another decay mode. So these singly charged Higgs can also decay to a standard model Higgs and a W gauge boson in part of the parameter space. So if one considers these decay modes, then for a very high V delta, so let's say V delta 10 to the power minus 1, this is what one would obtain. And for V delta 10 to the power minus 4 GeV, this is what one would obtain. So here, what happens that only this W plus HW actually contributes. Contrary to that, for V delta 10 to the power minus 4 GeV, both L plus HW and W plus HW can actually dominate. Okay, so there are 2 distinctive different regions that is possible to obtain. I have just one slide for lepton flavor violating signature. So because of this interaction, LL delta interaction, this doubly charged Higgs can mediate this lepton flavor violating process at 3 level, and therefore one can obtain very tight constraints. So here we have considered the doubly charged Higgs mass at 1 TeV, and we have varied the diagonal coupling between 0.1 to 0.3. And this is the region which is perfectly consistent with tau going to 3 mu surge, tau going to 3 E surge, then mu going to E gamma and other lepton flavor violating surge. So roughly, if the Yukawa coupling is less than, let's say 10 to the power minus 2, then for 1 TeV mass, it's sort of like okay. Now I have 3 or 4 more slides on different other models, and this is one of the very interesting proposal that I found in this paper. So where the idea is that the standard model Higgs can actually give rise to lepton number violating signal through this decay mode. So this is in the context of left-right symmetric model. So as we know that in the left-right symmetric model, there is SU2R triplet. Now this SU2R triplet mix with the standard model Higgs. So this is the mixing. And then these 2 right-handed neutrino can actually be pair produced if kinematically allowed. And this right-handed neutrino can have 3 body decays. So these are the 3 body decays because WR is very heavy. So at the end of the day, one has 2 same sign lepton and 4 jet final states, or even more exotic, 2 this delta R can be pair produced that can give rise to 4 right-handed neutrino. And from 4 right-handed neutrino, one can have 4 same sign lepton and multi-jet final states. So this has been looked into this paper, the first signal, and this is a summary. So along the y-axis, it is the mass of the right-handed neutrino. So as you can see, this is really very, this is relatively lighter. So between 10 GeV to 60 GeV. So it only works in this mass range, for this mass range. And along the x-axis, it's the right-handed gauge boson mass. And this sine theta is basically standard model Higgs and BSM Higgs mixing angle. So as we can see that sine theta mixing angle, if it's around 10%, then the right-handed gauge boson, which has mass around 5 TeV, can actually be probed with 2 sigma significance via this kind of a channel. The other interesting aspect for the left-right symmetry is that this delta R or this HR++, this is a doubly charged Higgs, which is a part of delta R. It can not only decay to same sign lepton, but this is another distinctive decay mode. So it can decay to same sign gauge boson, and this is the right-handed gauge boson. Now, it can have, if not kinematically allowed, it can actually have off-shell decay. So the total decay width will be same sign lepton and this off-shell decay. But in part of the parameter space, it might happen that this decay mode is actually dominant than this one. So this is for this plot sort of like portrays. So this is along the y-axis, it's this Yukawa coupling, and along the x-axis is the mass of the doubly charged Higgs. These are the different branching ratios for the 2 same sign lepton. So this is 99%, this is 90%, this is 50%, and so on. And these are the different decay width. So the decay width varies from 1 millimeter to 1 meter. Now, this part of the decay width is dominated by this HR++ going to L+L+. And on the other hand, this vertical line corresponds to the decay width where HR++ decays to 2 off-shell W gauge boson. And this has been looked into this paper by Bhopal and collaborators. And the very nice feature that they brought into is the complementary between the prompt search and the display search. So this is the coupling versus mass of the doubly charged Higgs plane. These are the prompt search, which are sort of like sensitive towards larger Yukawa coupling because they look into this HR++ going to E+, E+, mu+, mu+, displaced dilepton events. On the other hand, this display search, so which they looked into, is most sensitive if the coupling is relatively low. So they got the most sensitivity if the coupling is around 10 to the power -7. So here is the summary that prompt and display searches are complementary. And not only this, indirect search, for example, lepton flavor violation, neutrinoless double beta decay, they are also complementary to displaced dilepton search. And the other interesting aspect is that this search is very much insensitive to light neutrino mass hierarchy. So this is for inverted hierarchy and this is for normal hierarchy, which looks exactly the same. I have only 2 more slides to touch upon the type 1 seesaw and gauge B minus L, and then I will conclude. So the type 1 seesaw or the inverse seesaw, as we know, is the most simplest model, and that has this term, this L bar H tilde NR. Now what it does is not only it change the standard model Higgs decay width, but it also gives one of the signal that actually the CMS Atlas they have looked into. So here is the thing that standard model Higgs decays to light neutrino, right-handed neutrino, and then in the final state, this right-handed neutrino decays off-shell decay. So it can give rise to 2 lepton, 2 neutrino final state. And existing search for standard model Higgs can be utilized to constrain this right-handed neutrino sector. So this is the active sterile neutrino mixing versus mass of the right-handed neutrino plane. And this was the limit from 8 TeV search. Rather, I will focus on this. So this is the high luminosity discovery prospect with 14 TeV center of mass energy and 3 autobahn inverse luminosity. And active sterile neutrino mixing square roughly 10 to the power -5 is possible to prove. The final slide that I have, that the displaced decay of the right-handed neutrino can also be looked via this channel. So the standard model Higgs is produced. This is in the context of gauge B minus L model, and it produces 2 right-handed neutrino, and then right-handed neutrino decays to unmu JJ final state. The benefit that this model actually has, it does not, the production of the right-handed neutrino does not depend on the active sterile mixing. Rather, it depends on the standard model Higgs and BSM Higgs mixing. But the decay of the right-handed neutrino depends very much on the active sterile neutrino mixing. So the decay can actually be displaced. And the main important point that I would like to emphasize here, that this was the seesaw favored region. Now, if I look into the discovery prospect at the HLLAC, so the seesaw favored region can actually be accessed at the LHC or HLLAC. So this sort of like ends what I wanted to discuss, and I think I will stop here. So the summary, you can have a look. Okay.
Thanks, Professor Mitra, for a wonderful talk. I think we can take one or two quick questions. So if anyone has a question, please raise your hand. Okay. Professor Ranjan, can you ask, please?
No, I just clapped.
Oh, sorry. Sorry, I just got confused. Okay. So, okay, I don't see any other.
There's a question by Sabila.
Oh, sorry. Yeah. Please ask, Professor.
Hello, good evening.
Hello.
Yeah, ma'am. Ma'am, I have a doubt in a slide 10. Could you please open it? Slide number 10.
Yes.
Yeah. So, ma'am, could you please explain the last sentence? This large Y delta implies there is a large favor violation.
Yeah, so basically what I want to say is that this one, right? I mean, yeah, so this is, for example, the lepton favor violating signature, right? And let's say this can be tau to 3 mu or even mu to 3e. Now, in these two different vertices, this U-core coupling is actually sitting. So if you have a large U-core coupling, then you have a large contribution, right?
Yes, yes.
Yeah, so that's what I mean.
Okay. Okay. Thank you.
Okay, I think we can now thank the speaker and move to the next talk. So thanks again.
Thank you. Thank you. So I will stop sharing.
Yes,
okay?
sure.
Okay.
So next talk in this session will be given by Professor Rick S. Gupta. He will be talking about new approaches to cosmological selection of the weak scale. Professor Rick, please share your screen and can you please start?
Hi, can you hear me?
Yeah, I can hear. Please share your screen.
Okay. So let me try to share. Okay. Just 1 second.
Yes. Please.
I'll just try to like, yeah. So can you see my cursor first of all?
Yeah, I can see your cursor and screen. Can you just try to change 1 or 2 slides? Oh, it's working. Yeah, it's
can
working.
You see?
Yeah, it's working.
It's working. Okay.
Yeah, please start.
Okay, thank you very much. Okay, so first of all, I would like to thank the organizers for organizing this very nice workshop and for the invitation. I was asked to talk about relaxion models. So I've taken the liberty of interpreting this a bit more broadly. So as I will explain as I go on. So I will talk about relaxion-like models, because that I think is the most interesting development in this area, instead of focusing on like detail, like some new papers on some details of like the what is like narrowly called the relaxion models. So this is like really we are okay. So this is based on some work that I'm just starting with a student at TFR, the Chattopadhyay. So this is just, we are just at the very beginning stages, but so the talk might be more like a review, but of course I will outline what we are thinking, and maybe the presentation itself would outline that. So what I'm going to talk about is these new models, of which relaxion is probably the most prominent example, where the weak scale is selected cosmologically. And what I'm working on and what I will also try to present, the way I'll try to present is try to find what are the universal aspects and the universal signatures of these models. Although these models look completely different, the mechanisms are completely different. So, so indeed, like I don't think the other models would like to be called relaxation models at all. But let me go on. Oh, I can't move the slide anymore. What happened? Okay, yeah, it moved. Okay, so
it's not
the relaxation model.
Sorry, it's not changing.
Can you see?
No, it's not changing.
It's still in the first page. Okay,
Yeah,
let
it's
me.
still in the first page. You can try to reset it. Oh, now it's working.
Now what can you?
Yeah, now I can see your
okay,
second slide.
But it's hard to move. It's okay. So I had to press it. Okay, okay.
Yeah.
Can you see my second slide now?
Yes, yes.
Yes. Okay, so the relaxation model is a new way to address the hierarchy problem. So first, perhaps I should have say something about the hierarchy problem. I don't want to say much because most of all of you are aware of this. But I just want to make the point that because this is a conference about the theoretical perspectives a decade after the Higgs discovery, probably what is significant is how we view the hierarchy problem after a decade. Because as you know, the hierarchy problem says that the Higgs mass should be is expected to be not much smaller than the scale of new physics. And in some sense, there was no problem before LHC because, I mean, you could have seen supersymmetry or some signatures of composite Higgs models. So in other words, there could have been some new physics at the TeV scale that could have stabilized this. But now the LHC data seems to suggest that the scale of this new physics is more than the TeV scale. So now it becomes kind of a sharper problem. How can you have a light Higgs mass with a high scale for new physics? So we will consider approaches where you can have a light Higgs with actually no new physics, still a very high scale, which is unlike even supersymmetry or compositeness, where you do need some states at the TeV scale. So we are taking seriously, or these models are taking seriously, the LHC null results. Now, this is not to say at all, not to undermine at all the importance of like the continuing research on SUSY or composite models, or like continued experimental search for new physics at the LHC, because of course we should leave no stone unturned. We cannot assume that there's no new physics at LHC, and it's indeed very premature to say that there's no new physics at the TeV scale. But this possibility, maybe we can, after a decade of the Higgs discovery and discovery of no other new physics, maybe it is time that we start to at least consider the possibility that the scale of new physics is much above the TeV scale, and our notions of like our expectation that there must be TeV scale new physics, which came mostly from the hierarchy problem or solutions of the hierarchy problem. So maybe this is not correct. So this is just one possibility. This is not to say at all that it's not possible that we have come to a stage where we should say that there is no new physics at the TeV scale. So let me give you a picture. As I said, I want to focus on the universal aspect. So in all these models that I'm going to talk about, I'm going to talk about 3 examples, but as I'll show you, there have been many proposals. So what happens is that you imagine, so there is a landscape of solutions for this. So the Higgs mass in these models can take many different values, and either these different values of the Higgs mass can coexist physically in different parts of the universe. So different parts of the universe can have a different Higgs mass, or as maybe many people would say, the word is multiverse, but it's really different parts of the universe. Maybe they are not causally connected. So different parts can have different Higgs mass, as I've shown in these little blue blobs. So you see, maybe most of them will have Higgs mass close to M Planck because there is no symmetry. So, but there will be some, because there'll be some vacua where the Higgs mass, just statistically, there'll be some where the Higgs mass is at a much lower scale. For example, at the 100 GeV scale or something like that. So as I said, these different regions can actually exist, or these different possibilities can exist only as theoretical solutions, as will happen in some cases. It's not that they actually exist physically in different parts of the universe, but there's some way to scan through all these solutions. Okay. So then, of course, the second ingredient is that you need some kind of selection mechanism that selects the solutions where the Higgs mass is in some window. So is in let's say is in a window, let's say between, this is just an example, between 10 GeV and 1 TeV. So we need some kind of selection mechanism. Now, one idea has always existed, is this anthropic idea that, of course, the Higgs mass has to be in this region, because it's that is the only region where you that, like, if the Higgs wave was much larger or much smaller, you could not have had life. And this was an argument made in this paper that I've referred to below. But this is kind of I can go into the details, but this is kind of not like, there are arguments against it. For example, like it really is. So I don't want to go into it, but this is not completely satisfactory for many people. So like this anthropic argument. So now these new models are so they propose non-anthropic cosmological selection mechanism. So there's some dynamical selection mechanism, and as you will see, which selects this window. Okay. So relaxion model is, of course, one example, but there are many others. So as I said, these are not just relaxion models, and these other models, they have completely different mechanisms, phenomenology, they're completely different. But what I want to focus on is we'll explore if there are some universal features and signatures. So in fact, yeah, that is because, like, maybe if you just look into relaxion models, or because, to be honest, these are not as mature as, say, SUSY or compositeness or anything like that. So to take very seriously one specific realization of this idea may be a bit like taking it too seriously if you go to look in detail about the signatures and all, whereas there are many open issues with these models. So maybe the a more interesting thing can be to look at some broad features shared by all these models. So some broad experimental signatures. So, and this is another feature that, unlike the usual multiverse anthropic picture, where one of the main problems people have is that there may be no experimental signatures. Here, you will see some very concrete experimental signatures in these models, and I will highlight some universal signatures shared by all these approaches. Okay. So the first universal feature, in fact, the way so in all these models, what you have, these models are very simple. So you have the Higgs and some new scalars, which are typically very light, and it's the dynamics of the scalars that gives you the selection mechanism that selects the weak scale. For example, you might find that unless the Higgs is in a certain window, the scalars are not stabilized properly in their vacuum, or the scalars are not at their minima. For example, or the scalars don't have an unbounded potential, or they don't stabilize properly. So okay, please let me know if the slides are not changing or something like that. So there have been many papers, and mostly there have been many papers, and even this is like probably not completely exhaustive, but I mean, not many, but like order 10 or 12 papers, but on these various different approaches. Of course, number 3 is the original relaxion paper, and I'm not writing telling you about all the relaxion. There have been like maybe order 100 papers on the relaxion, but I'm just giving you the original paper, and then the other papers are really other approaches. They're different approaches to cosmologically select the weak scale. And mostly these are from last decade. So in some sense, this is a reaction to what has happened since the Higgs discovery. Of course, there are a few, only 2 papers by Dwali, which are before the Higgs discovery, but everything else is after 2015, most of these papers. So we'll focus. I'll, as an example, consider three of these models in detail. So including the relaxion model, and because these 3 are somehow representative of 3 classes, let's say. I mean, these are not the first. Okay, so I will talk about the others also briefly, but these are the 3 we'll focus on. So we'll focus on, of course, first the relaxion models, which were among the first proposed. So apart from those 2 papers before the Higgs discovery, this was the first proposal of this kind. Then there are 2 very recent papers by D'Analio and Teresi, and then which this proposal they call sliding naturalness. And then there is another class of models, and I'll discuss one of them. I don't know how to name this model, but it's a paper by Chung and Saraswat. So I'll call it the Chung-Saraswat model. Okay, so let me start with the sliding naturalness idea of D'Analio and Teresi. So again, it's a very simple model. You have it's like a 2 Higgs doublet model. You have 2 Higgs doublets, and then you have 2 scalars, phi plus and phi minus. Okay, so now the 2 Higgses, there's a specific kind of 2 HDM potential with this kind of a Z2 symmetry where H1, H2, if you take H1, H2 to minus H1, H2, so either H1 or H2 can be odd under the Z2, then the potential doesn't change. So in other words, you don't have terms like H1, H2, H1 dagger H1 or H1, H2, H2 dagger H2, something like that. Okay, so the reason will become clear why they have this specific kind of 2 HDM. But more importantly, you have these 2 scalars, and they have some kind of potential, and although it's actually the potentials they choose are quite generic, like they can be realized in quite is not a very contrived way. They can be realized in, they give some examples of like SUSY models and etc. that can realize this kind of thing. So in both, both for the phi minus and phi plus, there is the quartic has this parameter delta, which is a bit less than 1, but this can be again realized in a natural way. That's what they claim. And you can see that like both the potentials are almost the same except for the sign of the cubic term here. The feature of if you plot the first potential, let's say on mathematics or something like that, you will see that it has one shallow minima and a deeper minima, and the deeper minima is at a higher value of phi minus. The phi plus at this point only has one minima, and it's quite a deep minima. Now, what we'll do is that, as I said, you have in these models you have the scalars, and now they need to like talk to the Higgs sector in some way. So you add this kind of what they call a trigger term. This term is what triggers everything. So there's a trigger term. There's a coupling between these scalars and H1, H2, the Higgses. So now, let's do something. What we'll do is now. So now this trigger operator, this coupling between the scalar and H1, H2. So when the electroweak symmetry breaking will take place, H1, H2 will get some value order V squared, right? So maybe there's some sine beta, cos beta, but let's ignore that. So some value order V squared. So now let's crank up this value of V squared. So what we want to, as I said, that these models will select a range for the Higgs mass or equivalent to the V squared, because the quartic is fixed. So the Higgs mass, whether I say I'm selecting the Higgs mass or the Higgs wave, is the same thing. So we imagine again, so in these models, indeed, you have to imagine there are different regions of the universe with different values of the Higgs mass. And then what happens in these different regions, we want to classify that. So if V is 0, this is the picture we have. Now I increase V, so I now take the Higgs mass, which is 2 lambda V squared, between this, in this nice window that will become the good window for us. And in this window, what happens is, because of the addition of this term, first of all, if you compare from this one, first of all, what has happened is that the shallow minima for phi minus has risen a bit. But more importantly, now I have a second vacuum for the phi plus. Okay, so now I have a second shallow vacuum for the vacuum for the phi plus. Okay, going ahead now, if I increase it beyond this mu b squared, what happens now that the phi minus vacuum rises even more, and now you only have a deep vacuum for phi minus. Okay, so only in this window, in this window between mu, where 2 lambda v squared rise between this range, only in this window, both the phi's have a shallow vacuum. Okay, now sorry, I'm going in the opposite direction. Okay, now what is the selection mechanism? Let us come to that. The selection mechanism is such that only if both the scalars settle down in the shallow vacuum, only then those regions of our universe are selected. What happens in the other regions? In the other regions, if even one of the scalar settles down in the deep vacuum, what happens is that you have a total negative vacuum energy, and these regions of the universe undergo big crunch, like the opposite of a big bang, they collapse. And that is just because of the way, that is just because these minima are far too deep. And if you go into one of these, that would mean that your total vacuum energy is becoming negative. So you must have both the phi's in the shallow minima. Okay, and this means that if the V is 0, then phi plus doesn't have a shallow minimum, so it must settle down in the bottom. So there will be a big crunch. If V is very big, again, then phi minus does not have a shallow vacuum. So only in this sweet spot, only in this window where the V lies between these two masses, that can you have vacuum. So now let's go back to our picture. We have different. So in this model, you really need different regions of the universe, and they don't say how you generate this. Maybe through internal inflation or something. You have different regions of the universe with different Higgs masses, and these are causally disconnected regions. And then the regions where the Higgs mass is not in this window, and this will depend on the parameters you can choose, so that mu s and mu b is something reasonable. And then only this region encircled by this red thing, only these vacua, only these regions survive, everything else collapse. And this process of collapse, this all takes place after inflation during radiation domination. Indeed, they have a detailed discussion of the dynamics of how long will it take for the phi to roll to this minima with this at this temperature, and like they discuss all this in detail, and this puts some constraints, etc. I don't want to go into all the details, but it's just to say that they do a convincing job of like looking into, like, it's not just they do look into all the details and show that everything works. Okay, now that was one example. Now I'll go to the relaxation mechanism, and I will this is of course the most mature of these models, and you will see that why this achieves something that none of the other models do. And that is namely the fact that you do not need all these different regions with different Higgs masses, so you don't need this kind of multiverse at all. So here you really this will become clear soon. So here what happens that the Higgs mass squared, let's say the mu squared of the Higgs potential, depends on the value of a field phi. So let me see how much time I have. So how much time do I still have?
You have 10 more minutes.
Okay, so I will try to be quick. Okay, so maybe I will not go through the third example and then just go to the universal features. So in these models, the mu squared of the Higgs depends on the value of the scalar field phi, and the scalar field phi have this potential where it's rolling. So this will become clear in the next slide. So you have some kind of, you can have also, here I've shown a linear potential phi, but you can have a phi squared and so on. And what happens is that, as I said, the value of the Higgs mu squared depends on the phi, and I've made this dashed line. On the right of this dashed line, the mu squared is negative, so the Higgs has a wave. And on the left, it's positive, so the Higgs doesn't have a wave. So imagine that the field starts rolling from the top. I should have made something there. And then when it reaches this area, the Higgs gets a wave. And when the Higgs gets a wave, something else happens. You trigger a new part. This is like the trigger operator. You trigger a new part of the potential that depends on the Higgs. So there's an oscillatory, like a cosine potential, which is typically like what you can get from an axion or something like that, which gets triggered only when the Higgs gets a wave. So once the Higgs gets a wave, you have this kind of oscillatory trigger, and that stops the rolling. So recall that the rolling of this field phi, and this is all happening during inflation with Hubble friction. This is just like a ball rolling down a hill, and it will stop when it reaches the barriers. So this is the same equation of motion. So, and the stopping condition is, as I said, that you have to come to a minima, and then you can minimize the potential. You had the linear part, the g lambda cube phi, you take a derivative of that, and you have the cosine part, and I've just given you, and you can show that and you get this condition, and you can show that if you take this G that was a coupling in the relaxation potential small enough, you can create a hierarchy between the cutoff lambda, which is the bare, which is like the cutoff for the Higgs mass, and V. So going back, if you look at the two terms here, the first, if you look at the two terms, you have a lambda square term and a g lambda phi term. What is happening is that the first term is, of course, a constant, and this can be big. It can be like 10 to the 10 GeV or something. And the second term is changing. So the second term is changing, and whenever both of them become kind of equal and you go from positive to negative, something happens and it stops the rolling. So in some sense, the universe is doing the tuning for us. So because the phi is rolling, and only when the Higgs mass is at a very small value, it stops. So that is the mechanism. And so the nice thing about this is that, of course, now if you look at all the vacua, if you go down in more realistic relaxation models, you will actually have also a global minima. It will not just keep going down. So if you go to the other, most of the vacua actually have mh square order lambda square. It's just that you select the vacua with the low Higgs mass through this dynamical mechanism. Okay, so it's and all these vacua don't coexist in this case. Okay, so they it's not that you need to have a multiverse or anything. You just can settle down only. It's not that the other vacua actually need to exist, because the scanning is happening in time. So you're scanning through time across these different Higgs mass, and you don't even reach the heavier Higgs masses. You stop before you reach that. So this is, in that sense, a very nice mechanism, because you don't need all this multiverse or something like that. Okay, so I would just like to say one thing. So how is this back reaction potential coming? It comes in this original paper by Graham, Kaplan, and Rajendran. What they suggested was that the relaxion can be like the axion of a new strong group, like a QCD prime. And then what they did is that they made the axion potential dependent on the Higgs. And the way they did it is that they had this fermions. This L is like an electroweak doublet. These are vector-like fermions, and N is like a singlet. And you can see that the axion potential usually goes something like this. You have the lightest fermion Mn, F pi prime cube, and then a cosine term. Now the Mn, the lightest fermion here, gets a contribution by integrating out the L, which is Higgs dependent. So there's like a Higgs dependent seesaw contribution. So in the end, you get a, sorry, I know I'm rushing through this a bit, but in the end, you get a potential which, so the mass of the N gets some Higgs dependent contribution when you integrate out L. And so you get a potential which depends on the Higgs wave. So that is how they achieved this thing. So now there's the other model. So
you have 5 more minutes. Okay.
I have 5 more minutes left. So, okay, let me just briefly describe this model. This is like another class of models, and it is actually also very interesting, where you just add this term B phi, this term. Again, the Higgs mu square depends on the phi. And now what you can do is, this is a very simple exercise. It's just the simplest case, a Higgs and a scalar. And you can look at the potential for the phi that you get once you put the Higgs to its wave. Now, the Higgs wave depends on the phi. So it's not very difficult. You can do the exercise. So the Higgs wave is, as is written here, is just the phi dependent mu squared over 2 lambda. And then if this mu squared is positive, the Higgs wave is 0. And if you go back here, so if the Higgs wave is 0, the phi, there's no phi dependence at all. So the phi, so when you put the Higgs wave to 0, the potential has no phi dependence. If you do take into, if the mu squared is less than 0, then the Higgs will develop a wave, and then you get this simple potential. Okay, now if I plot this potential, it has this very nice feature that just when the Higgs, just in the region between, so again this line separates the region with no Higgs wave versus the region with a non-zero Higgs wave, and this potential turns just at that critical value point. Okay, now of course you can try to ask what happens, and this is really a very simple model, as I said. Now you have this B phi H dagger H term, and you can close the Higgs loop, and you'll get a new contribution. And if the Higgs loop is closed at a mass scale close to the Higgs wave, you can show that the maxima of this potential, now it's not the minima, it's the maxima, lies very close to this region, this dashed line where the Higgs, so the maxima lies at a region where the Higgs wave will be small or close to 0. And now you can, of course, it's hard to be on top of a maximum. You can add another, just like in the relaxation case, add an oscillatory potential. And then you can create, again, a landscape of vacua. Again, if you move away from the dashed line, on the right-hand side, the Higgs wave is 0. But on the left-hand side, if you move away, you go to higher and higher Higgs masses. But the highest point is a point where the Higgs mass is actually light. Okay. How can you, so this is again, how can you use this fact? How can I use, I just have a few slides left. So how can I use, I mean, is there a way to select or a mechanism to select the vacuum at the maximum? And yes, as there was a talk on inflation, and as it was nicely described there, inflationary expansion is a way to do that. So in inflation, typically, again, the universe will have different causally disconnected patches. And the value of phi can typically, because of quantum fluctuations, can be different across these patches. So imagine there's a patch where phi is at one of the lower vacua and another patch where phi is in the higher vacua. So because inflation, the expansion depends on your volume, vacuum energy, at the higher point will expand much more, will become exponentially larger because of inflation. So the red patch here, which corresponds to the red star, there will grow to exponentially larger volume than the green one. Okay, so this is the way they select this thing, these vacua. So now let me quickly go. To what I'm trying to work on. So as you saw, these three models are completely different. They're completely different. Their mechanisms are different, but there are some nice universal features. So I will try to go through these as just a few more slides left. So this is I am given the wrong reference. This is actually the work that I'm doing, and it's in progress. So the three universal signatures that you will see is that in all these models, you need new states. For them to work properly, you need new states at the TV scale. This might be a bit confusing because I said at the beginning that I want lambda to be much higher, Higgs mass to be much lower. So that is still true. These new states are not cutting off the Higgs quadratic divergence, but it's a different, not colored. These are new states not related to the Higgs mass. Then the second feature, and all these three features have nice signatures, okay? And the second feature is that you need light scalars that mix with the Higgs. So you have Higgs portal kind of constraints, as was also discussed in one of the previous talks. And the third feature is that these models typically can give rise to dark matter because they can oscillate about the minima and give you coherent wave like dark matter. So point number 2 and 3 I can go through in 2 minutes. So it's just the first point. So it's just I would need a few minutes for point number 1, and then I'll be done basically. So point number 1, why is it that you need new states? Because this is a key point, I think. New states at the TV scale, and again it will be so it's because this trigger operator that you need that connects the scalar to the Higgs. This trigger operator has this kind of H dagger H kind of thing, right? Now, when I will close the Higgs loop, I can get an Higgs independent trigger operator, right? I can close the Higgs loop. Let's say the Higgs loop, the scale that cuts off the loop is, let's say, M. So I will get a trigger operator without the Higgs, and that is dangerous, right? Because the whole point is that the Higgs gets a wave and it triggers something in the dynamics of the phi that selects so that says that the Higgs must have a wave and it must have a small wave, otherwise the dynamics of phi gets messed up or something. So if you have a Higgs independent trigger, that whole mechanism can get spoiled. So that's why this shows that you need the scale M to be not much above the weak scale, because then the Higgs independent part will become bigger, and this means that this is typical to all these models for very different reasons, but for this basic universal reasons, but it's realized very differently. So this M less than 4 pi V means that you must have new TV states, but so I should say that this doesn't mean that the Higgs mass needs to be cut off at M. The good example is the example I gave you of the relaxion of this. That's why I had to go through this in some detail. This term M tilde squared, the relaxion wiggles that can come from making the relaxion an axion of another strong sector. There, if you close the Higgs loop, you won't go up to the scale at which the Higgs mass squared is cut off, just because the potential cannot get contributions from much above the strong scale of the new group, because as you know, the axion gets contributions from non-perturbative effects, and if you go to scales much higher than that, this will just be cut off. So you can have an M that cuts off this H dagger H within this term much smaller than the cutoff for the Higgs mass H dagger H term. Okay, so this is or I mean, of course, there's another option. You can have a trigger which is not H. So that is why this other paper went through the trouble of having a 2 Higgs doublet model, because they didn't want this problem that you can close the Higgs loop. So they had a trigger like H1 and H2, and they also chose a potential where you cannot close this H1 H2. So if you had an H1 H2 H dagger H term, H1 dagger H1 term, let's say, then you could have a 2 loop generated some sensitivity to like the to the high cutoff. But either way, whether you have this M at whether you have these new states that cut off the Higgs divergence, or you choose something like this 2HDM option, you have new states, new TV scale states. So in the case of the relaxion thing, you have this new vector-like doublets, which are not colored under QCD, but they are electroweak doublets, so you can produce them at LHC and so on. And in the 2HDM case, of course, you have a new charged Higgs and pseudoscalar. So there will be some TV states which are maybe not, and this is true for, I showed you 10 or 11 papers. This is true across all the papers, not just these 3 models I'm considering. And so the new charged, so this is a nice feature. Okay, so now I'm really done. So the other things are very easy to explain. So the other thing is that once you have this trigger operator, you will induce some mixing between phi and the Higgs. So because the phi couples with the Higgs, and even if you have something like a cosine which is a phi squared, you will still induce the mixing because the phi kind of is not at its minima. So phi also has a web. So once you give the phi and H its web, you will induce a bilinear H phi mixing term, and that gives you a mixing between H and phi. And so for the relaxion, we were the first ones to, one of the first, I think, to point this out, and we found the constraints over a large range from sub-EV masses of the relaxion to, so this is the mass of the Higgs portal scalar. So the relaxion has become a Higgs portal scalar to the GeV range, and depending on the mass range, you could get bounds from LHC, LEP, beam dump, flavor experiments, cosmological probes, fifth force, etc. And this is just a summary of all the bounds. I can't of course go into all this. Depending on the range, like in the MEV scale, most of the bounds are beam dump, etc. In the KEV scale, they came from astrophysics and cosmology. And in the very sub-EV scale, fifth force was the strongest bound. So this we have done for relaxion, but this will exist for all the models, which has been indicated in some of these papers. But I think what I would like to do is find if there's some universal predictions for where in this parameter space these different models lie. And the third universal feature is this is my last slide, is that in all these cases, you have the scalars which are quite naturally through the mechanism they will be in general displaced from their minima. So they can oscillate, so they will oscillate about their minima, about this minima, and as is well known, this oscillation, these are damped in the right way to give you behavior which is just like non-relativistic dark matter. So this is just like axion dark matter. There is the possibility of what is nowadays called wave-like dark matter. So this has been in fact studied in quite I should have written the paper. It's a paper by Gilad Perez, Abhishek Banerjee, and Hoong Jin Kim. So I forgot to put the reference. This has been studied for the relaxion, and it's also mentioned in the papers on the sliding naturalness. But again, I think there is some kind of universal aspects to be uncovered here, maybe like whether it's the same mass range and so on. So it's, I think, very intriguing that all these different models, which are very different, although their basic principle may be similar, that they give this kind of universal signatures. And the 3 universal signatures I've talked about are TV scale states, which are not related to the Higgs H dagger to the cutoff for the Higgs mass. So that cutoff can be much higher. And then all these scalars, the new scalars introduced always have a mixing with the Higgs in all the models I have seen, at least. And then because they can oscillate about the minima, they can give you some kind of coherent dark matter. Okay, so that's it. Thank you.
Thanks, Professor Rick, for this interesting talk. Okay, we are already running late. So if there are some questions, we can take one or two quick questions. So please raise your hand. Okay, I can see Suvadeep. Suvadeep raised his hand. Suvadeep, please unmute and ask. Hello, Suvadeep, we cannot hear. Can you please ask, unmute and okay. Okay, he has written in the chat box, so I'll read for you the
Yeah,
question.
I can see in the chat. Yeah.
Yeah. Okay. You can see. Then you can just answer, please.
Okay. Let me just try to because just 1 second. Let me read it. Thank you. Okay, so yeah, so you have asked is that how exactly are they getting cancelled? So maybe let me give you in the example for the relaxion. So they are not getting cancelled actually. Just 1 second. So yeah. So for the relaxation, for example, I have the Higgs mass has a lambda squared, and this bare lambda squared contains all the loopers. For example, you can have a stop or whatever at 10 to the 10 GeV. That will correct the lambda squared. So indeed, the fact that I'm not choosing the lambda squared to be weak scale means that this is absorbing all the quantum corrections. What is happening is that I have two terms, which because here, if I didn't have time to describe in detail, but the phi gets a field value of order lambda by G. So both these terms are of order lambda squared. And what is happening is that these terms are canceling each other, but through some dynamical mechanism. But indeed, the loop corrections due to new heavy states are not being cancelled by anything. That's why they are all going to this lambda, because this lambda squared can be much, can be a very large scale. This is for the relaxion, but in the other cases, where you have this kind of actual physical landscape of possibilities, there again, it's not cancelling. So you have, but this is just like the multiverse idea that people have, but now realized in a dynamical way. So here again, as most of the vacua probably have a Higgs mass value, which is very close to the cutoff or Planck scale or whatever, but just statistically, there will be, because you are always allowed to tune, just because of tuning, there will, so let's assume that the different parts of this multiverse or different parts of this universe has different values for the parameters. In some, because if you have hundreds of these, just or millions, or I don't know how many you need, just accidentally you will have a light Higgs mass. That is this is literally tuning. So because it's tuning for in a very small region, you will have light Higgs mass. But then there's a mechanism to choose this small region as our region. That is what is happening. So indeed, there is in that sense, it's there is no cancellation of the
Okay, I think we can thank the speaker now and move on to the next talk. Okay, so
okay.
Thanks again for this wonderful
Thank
talk.
you very much. I'll stop sharing. Yeah.
Sure. So the next talk will be given by Professor Srirup Rai Chaudhary from TFR. He will be talking about future directions in particle physics. Please, Professor Rai Chaudhary, please share your screen and maybe you can start.
Yeah, I'll do it.
Okay, so I'll inform you after like just 10 minutes before your time. This is 45-minute talk, so I'll inform you after 35 minutes.
Yes, that is fine.
Yeah. Yes.
Can you, has it gone full screen?
Yeah, it is full screen. You can try to change one or two slides so that I think if we can see it.
I'll do that. If it doesn't happen, we'll see.
Okay. Okay. Yeah, please start.
So thank you, and I'd like to thank the organizers, Anand, Sudhir, Biplav, and Ranjan, for inviting me to give this talk. And I will be talking, or at least try to talk about, future directions in particle physics Now, of course, I should be honest at the beginning and say that this is something about which I don't know anything. I know quite as much as this gentleman you see, and I don't even have a parrot to pick out the right choices for me. So what I will do instead, I will just read to you from all my little booklets and ask you to take the job of choosing. But so I hope you will sort of get an overall picture, and I will also try to keep the talk free of mathematics as far as possible, and just show pictures and discuss ideas. Perhaps that is more needed since you've had a very heavy day of various kinds of technical talks. So without more ado, let me start. So what I will be talking about, just give me a moment, I can remove this. Yeah. So the outline of, so first I will talk about, I'll talk about this pillar, what we do know, this what I call the 7 pillars of our understanding. Then I will also talk about the 7 hurdles in our understanding. Then there are 7 important things which we do not know. After that, I will look at the different approaches to try to understand what we do not understand. Then, of course, those different approaches mean a lot of hypotheses, and we'll quickly look at experimental tests of these hypotheses. Then I'll come to the speculations which are being made now, which are fueled by experiment. Finally, I'll say something about future experiments, possible outcomes of those experiments, and I'll end with by talking about what I think will be the trends in particle physics in the years to come. So let me start with the 7 pillars of our understanding. So the very first pillar of our understanding is that we understand that elementary particles interact through gauge theories. And that's what we call spontaneously broken gauge theories. And here is the wonderful proof of these gauge theories. It comes from the Hera collider. This is based on the full data. And you see that the neutral currents due to the Z and photon, and the charge currents due to the W, so these are the ones, they match in strength at a mass which is just about the electroweak or the Z mass. So at this point, they become the same interaction. It's a beautiful example. You see that we do have, so unification of electroweak unification does occur, and you see that the breaking of the symmetry gives you this difference here. So that's the first and most important pillar of our understanding. The next pillar is that to explain why the symmetry is broken, there is a Higgs boson. So we now have no doubt at all about the Higgs boson. We have a signal to many sigma, and that, of course, is the Higgs discovery. So this is the Higgs resonance in blue, the Z resonance is in red. The third pillar is the fact that the Higgs coupling to the most of the particles is almost precisely as we expected. So here is the plot from CMS, and you see that the errors are rather small except for the muon. And even if you compare them on a separate graph with the standard model, they almost match. And of course, the couplings are proportional to the masses. So if you measure the masses and the couplings, you will expect to get this straight line. So that's the third important pillar, that the Higgs sector is more or less as we had thought. The Yukawa couplings are the source of the fermion non-particle masses. The next pillar is the fact that the fermion mixing, we talked about the fermion masses, the fermion mixing matches the CKM mechanism very precisely. So this little circle here is the level of our uncertainty in it, but we have this nice unitarity triangle to show us that there is CP violation of the standard model, and it is matching with what the CKM mechanism predicts. Now, I should also tell you that when I started research some decades ago, this yellow circle was the allowed region. So the experiments have improved to the extent that those yellow circles have now shrunk to this little ellipse. 1 sigma and 2 sigma ellipses you see there. The fifth pillar is that when we look at the global electrowave fits, this is to 21 measured parameters, we are accurate within 2.4 sigma, with the large errors coming only with parameters which are very difficult to measure. So the entire electrowave model seems to be working very nicely. And this is reinforced by when we look at the cross section at E plus E minus colliders, C plus E minus two hadrons. You see these beautiful data, including the data at the Z resonance and then later at LEP2. In a college or school, if somebody got data like this, then you would surely make use of fudging the data. But these are real data and it matches the theory very, very beautifully. So that's the sixth pillar. And the seventh pillar has to do with the QC decoupling. And that also evolves exactly as expected over at least 3 orders of magnitude. All the data lie almost exactly on this curve with the 6 quark model. So there are 7 pillars, and we thought of, based on this, can believe that we understand our world quite well. But there are also 7 hurdles in our understanding, and these are things which we do find difficult to understand or to fit in with what we know. So what are these hurdles? The very first, of course, is the question of what is dark matter. So you see here a picture. This is a very recent picture from the James Webb Space Telescope of an almost perfect Einstein ring. And this is caused by some dark matter, not this star from our galaxy, which is right in front, but from some dark matter object, which is somewhere in front of whatever is creating this Einstein ring. So, of course, it's a wonderful proof also of the bending of light, but it also shows us that there is dark matter in the universe, and there are other proofs also. But of course, we don't know what it is. That is the bottom line to everything else. The second question, of course, is what is dark energy? And here again, the supernovae data from faraway galaxies tell us that at large redshift, universe seems to be accelerating rather than slowing down or remaining expanding uniformly. And we have no clue what it is, unless you can modify Newtonian dynamics, but till now nobody has got a model which really works. And then in that case, there is 68% of the universe is dark energy, again, an unknown thing. The next question is how to explain the baryon asymmetry. So of course, in cosmology, all matter is baryon. So electrons, except photons, everything else is baryons. So if you look at the asymmetry between electron and positron, neutrino and antineutrino, protons, neutrons, and calculate that number, difference between the particles and antiparticles, then you get a number which is called the baryon asymmetry. And the number to compare it with is the photon number, because these will grow and decay similarly with time and with the expansion of the universe. So what we find is that the standard model predicts a baryon photon ratio of 10 to the minus 18. And what is observed is 10 minus 10. So there is a discrepancy of so many orders of magnitude. Now, we also know the 3 Sakharov conditions to get such a baryon asymmetry, and I'll come back to this again. We will need baryon number violation in the early universe. We'll need CP violation. We will also require a non-equilibrium state, a situation at one stage. But what is important is that the CP violation in the standard model is what gives us this 10 to the minus 10. So it's vastly too small to explain the baryon asymmetry. As a result, we need some other source of CP violation. So though we have CP violation in the standard model, terrestrial experiments fit it perfectly, but on the cosmic scale, we just don't have enough CP violation. The next is a whole bunch of questions associated with the neutrinos. First of all, the question is, why are the neutrino masses so low compared to these are the masses on a log scale? So it's many, many orders of magnitude why the neutrino mass is so low. And even if they are so low, how are they arranged? Because we know the two differences, but we don't know the difference, which one is which. Then there are other questions. Is the neutrino mass of Dirac or Majorana in nature? Do we have a no? This is the question I've already asked. Is there a right-handed neutrino? If so, a right-hand neutrino is a gauge singlet. So then how was it created from the radiation? When radiation and matter separated, how was this created? Then there is the PMNS matrix, which is the mixing of neutrinos. Does it have a phase? If so, how can we measure it? And 4 questions, are there more neutrinos? In particular, is there a fourth sterile neutrino? So there are associated questions, but on the whole, this is another area, gray area for us. All right. So the discrepancy in neutrino masses, I should have shown you earlier, is also a very, very big number. Then we come to the strong CP problem. So what is that? A little detail here. The SU3 symmetry allows us to have a term like theta GG tilde, and which is of this form, where this is the field strength tensor of the gluons, and its contribution to the electric dipole moment of the neutron will be simply by dimensional argument. So this is these are field strength tensors, so dimension 2 each. So theta is dimensionless. So the electric dipole moment, if it's due to theta, will have theta in it. It will have the electric charge, of course, and 1 by the only scale we have, neutrino mass, the neutron mass. So that is 10 to the minus 14 e centimeters times theta. I forgot to write the theta. And the contribution to this, of course, will have to be. So there is something not showing here. So this is the experimental value. I should not have, should have changed this line. But what happens is that this is the experimental value, which is very small and which basically shows us that the neutron is almost perfectly spherical. There is very little deviation from sphericity, even though it has some detailed structure inside. As a result, there is a discrepancy once again of this very large number. Then I move on to the 6th problem, which is the question of whether the electroweak vacuum is stable or not, or is it metastable. So you heard a lot about this in the last talk, but let me just describe the basic idea here. That we know the potential, standard model potential. Now we know both mu and lambda because of the measurement of the Higgs mass. However, if we look at the evolution of lambda, we see that at higher scales, it goes down, and at one point it hits 0. The problem is that, remember that this is the mu squared term, and it goes up because of lambda. The weaker this term goes, the deeper the potential goes. So the lower lambda becomes, the deeper and deeper the potential goes, and when lambda reaches 0, the potential simply goes to minus infinity, which of course I cannot show you. So the vacuum would destabilize, and that would be horrible, because in that case, all particles would go down to minus infinity and emitting an infinite amount of energy. And that would, of course, depend, of course, it may not go to infinite energy, but it will certainly emit a lot of energy if there is another point, another minimum somewhere. And what we see here are only false vacua. But the data show us that we are on the cusp between stability and metastability. So metastability is dangerous. Stability, of course, would be fine. This is what we had always thought the vacuum. So, first of all, if the vacuum destabilizes somewhere in the universe, that will immediately go up in energy because of the emission of all of these things. The result, the neighborhood will get heated up, and that will again lead to the energy going up and further spread of this of the vacuum destabilizing. And eventually the entire universe could be engulfed in a huge explosion of energy coming from simply this effect. And that is been called the fiery death of the universe. Now, of course, this has not happened as the universe cooled from the Big Bang. Because at the Big Bang, it was certainly above these energies. But when it cooled, had this effect been true, then this thing would always have been true. The vacuum would never have been stable, and the cooling would not have occurred. So we are now in a sort of puzzling situation. And I will come back to this. But you see here, I'll quote from Einstein. Einstein had said that the Lord is subtle, but he is not malicious. But I will contend that the Lord is just a little bit malicious because he has left us on the cusp of absolute stability and metastability, and we don't know what will really happen to our future. Now, let me go to the seventh and last problem, that is the hierarchy problem. And what does that say? That if there is a heavy scalar in the theory somewhere, it could be some other particle also, then of course you will get the standard thing. I'm looking at dimensional regularization. You will get a term proportional to the mass of the heavy scalar, which is quadratic divergence, essentially, depending on the scalar. There's a logarithm which you need not worry about. But if there is physics at some scale like this, then what will happen is that this is the change in the Higgs mass, so it will get driven up to this ms square. So then Higgs will get driven up at one loop to ms. And so if ms, for example, is 10 to the 12 GeV, when the vacuum destabilizes, then you have to have new physics in order to destabilize it. In that case, the Higgs mass should be, but instead
sir,
it's 125 GeV.
So your voice
Yes.
is breaking.
I don't know what to do about that.
Okay, now it's fine.
Okay, I think it's the connection. Okay, let's just go ahead then. If it recurs, then tell me. So the mass of the Higgs is only about 10 to the 2 GeV. So again, there is a discrepancy of a huge number here. So not only do we have problems in the thing, but we have these huge numbers to explain. Moreover, there's a matter of details there. So in the standard model, these are not quite discrepancies in understanding, but again, there are certainly things which we would like to understand better. Because after all, the standard model has 21 free parameters. There are the gauge and Higgs couplings, fermion masses, 4 quark mixings, 2 QCD parameters, and 1 gauge fixed mixing parameter, which you need to do any calculation. So of course, so many parameters and their structure, because they do have a structure. For example, the CK matrix has this particular hierarchical structure, large along the diagonals, smaller when you go one step off the diagonal, and much smaller when you go 2 steps away from the diagonal. So there is a structure. Now that means that there must be a structure. These masses also have some structure. They become heavier as you go towards the third generation. Now, if you include neutrinos, then you have more problems because you again have a much greater range in these masses. You have another 7 parameters if there is a PMLS matrix with a phase. This is not understood.
Sir, your voice is completely gone.
I won't call it a hurdle. Okay, I'll do something. I'll try to shift to my mobile hotspot. So give me a moment. I'll stop the sharing. Okay, I'll reduce it. Let me see if I can go to my mobile hotspot and see if that connection works better. Can you hear me now?
Yeah, yes, sir.
Okay, let's hope this is. So now let me discuss the different approaches to trying to understand these questions. So I will start by, of course, seeing how to tackle the hierarchy problem. Now, if we only had the standard model and the Planck scale, which of course, where we know new physics comes in, then of course the hierarchy problem could be tackled simply by taking whatever extra contributions you have and cancelling them out using a counter. The problem comes when we have an intermediate scale, and that I've just discussed. So that intermediate scale tends to push the Higgs up to that scale. And now there are two ways to do it. One way is to do the following. So suppose is to reduce the scale of the new physics down to just above the standard model. So let us have some mechanism by which the new physics comes in at a scale just above the standard model, in which the Higgs may be pulled up to the new scale, but so what? It's more or less at the standard model scale. The other possibility, so there are these two models which do this. One is Technicolor. I will talk about this in a little more detail. And one is extra dimensions. They basically follow this idea to reduce the scale. Then the other possibility is that, okay, keep a high scale, but for whatever effect tends to pull up the contribution, you have another one which tends to pull it down. So there is a cancellation of these quadratic divergences. And the two models, popular models which do that, one of course is supersymmetry, as everyone knows, the other is the little Higgs models. So let's just quickly look at this. So in the Technicolor, of course, is perhaps the most natural way to go beyond the standard model. It's if the Higgs is a composite object just like the pion, then its binding energy will act as a natural cutoff for the standard model, just as the nucleon mass acts as a natural cutoff for the pion nucleon model. So the mapping you do is just like the pion, you have the Higgs. You replace the quarks by technifermion, which are new kind of fermion which will be sitting inside. And instead of the SU3 interaction, you just take a generic SUN interaction. You can put in whatever you like. Now the problem is that it has always been difficult to create a realistic model, because with the basic model you cannot give quark masses. So you created extended Technicolor. Then you found out that there was too much contribution to meson mixing. So you created working Technicolor. And finally, you found that it doesn't satisfy the precision tests. So you invented another thing called top color assisted Technicolor. Anyway, by making the model very complicated, you can actually evade all the experimental constraints and predict technipions, techniro, etc. really. So the major problem with these models comes from the fact that in precision electroweak tests, the Technicolor contribution to the S parameter, the change in this parameter, has this constant term 2 by 3 pi, plus things which you can adjust by taking up the scale. So you can make these small, but 2 by 3 pi you can't do anything about. And 3 pi is sort of close to 10, so this is like 0.2. And experimental error is already 0.07, so that is far below 0.2. So this is a problem with Technicolor, which you have to really make a lot of effort in order to solve. Then, of course, we have supersymmetry. Everyone knows what supersymmetry is. Bosons and fermions have partners of the same mass and quantum numbers. So for every contribution to the Higgs hierarchy mass, there will be a fermion loop, and the famous minus sign in the fermion loop is going to cancel out all of these terms. So you'll have a perfect cancellation if supersymmetry is perfect. If this fermion is much heavier, then of course you will have partial cancellation depending on how heavy the mass difference. So that of course is supersymmetry. And what supersymmetry lands us with is that in addition to the standard model particles, you now have this entire spectrum of supersymmetric particles, which we are of course trying to look for and have not yet found. I'll come back to that. Then I'll just make a quick survey of the ideas. The next idea is extra space dimensions, the two ones which solve the hierarchy problem. First is the idea that there are large extra space dimensions which are compact. So I've drawn this torus. So that's like a two-dimensional surface, which is the extra, which is compact. So, I mean, I can't draw it, it's all in higher dimensions. So there is something called the brane, which is a 1+3 surface, which is our ordinary Minkowski space. So in this theory, gravity becomes weak on the surface because it's only a small volume of the entire bulk and is strong in the entire bulk of all these. Effectively, in these theories, you can bring the Planck mass down to about 10 TeV. And so there is no hierarchy problem. Then there is another way of doing this, which is to create a warped extra dimension. So this warped extra dimension, which is drawn here, so there would be two such branes on either side. One is called the UV brane, one is called the IR brane. So the Higgs, and we also generally live on this brane. And the space-time between this extra space-time, it becomes smaller exponentially by this factor e to the minus kr phi, where phi is the angle which takes you from, it goes from 0 to pi, because this has the nature of S1 by Z2, which is S1 is a circle. So then that pi would go from 0 to 2 pi, but instead only goes up to pi. So it's a circle folded on itself. So if gravity is strong on this UV brane, it sort of gets propagated here and becomes small as a result of this warping. And effectively the Planck mass, though it is 10 to the 16 TeV to begin with, it picks up this factor of minus 11 pi. So phi will be pi here. You only have to keep kr as 11. And you would get again the Planck mass of the order of about 10 TeV. So once again, the hierarchy problem goes away. Then we come to little Higgs models. But this, like Technicolor, goes back to the pion for help. But it doesn't go back to the composite pion, but it goes back to the pre-composite days of the pion, some of which were discussed by Rohini in a talk in the morning. So in the sigma model, the pions are pseudo-Goldstone bosons. They're essentially Goldstone bosons, and there is a little bit of a symmetry breaking term which gives them a little mass. But which comes from essentially from the fermion masses. So we assume a new symmetry which is based on SU2 cross U1 to the end. So it's a big, large group. And that happens here. But this one breaks down to your normal standard model. And when it breaks down, the Higgs is the pseudo-Goldstone boson of this symmetry breaking. So it's massless to begin with. But in this model, you can show that the Higgs mass is generated radiatively. So because it's generated radiatively, it picks up this extra coupling, small coupling, and it becomes small for that reason. So it does not become too small. So this smallness is taken care of by putting things at this kind of level of mass. The nice thing about this model, which I have not drawn, is that there are extra bosons coming from the other SU2. You could even take it as SU2s. And the bosons come with factors in their coupling, which enables the contribution, the quadratic contribution to the Higgs mass from the standard bosons and from these new bosons will cancel among themselves. If you have new fermions, it will become fermion against fermion cancellation. So it's similar to supersymmetry, but also not similar. And remember that you cannot go very high in the scale. In supersymmetry, you can go almost up to the Planck scale. Okay, so those are the main attempts to solve the hierarchy problem. And then we come to the issues in the vacuum stability. So the first thing is this is how the vacuum, the lambda coupling, quartic coupling runs. So there is a dependence on the value of lambda, which is the quartic coupling, let us say whatever, and you'll have to fix it somewhere. And the Yukawa coupling of the top is very sensitive to that. It depends on the fourth power of that. Also on the gauge couplings and so on, but they are better measured. But as of now, you see, there are these two parameters, the lambda and the h star. The measurements come from, look at the mass and the mass of the, sorry, this should be empty, and the mass of the top. They come from the mass measurements. Sorry, HT measurement comes mass. And these have limitations. The mass measurements, of course, have limitations in their accuracy, and especially for the top mass, since the top is a quark and therefore there is no asymptotically free state of a quark. How you will define MT is a question. It is easier to define it from the cross section. So what we know from this is that even with the best measurements we make, this will not be able to resolve the issue of whether we have a stable or a metastable vacuum, because as you see, we are on the cusp and it requires very accurate measurement. What we need to do that is to measure both the lambda and the top Yukawa directly. So one of the ways to do that is to look at Higgs radiation from a TT bar pair, to measure the Yukawa coming of the top, and to measure the double di-Higgs production at the LHC. So these, of course, are things which people are trying very hard to do. And this will be needed. We will need to do that to understand vacuum stability. Now, there are some issues about metastability and the early universe. Suppose even if we have metastability, let us see what people have been speculating about. So long back in 1977, Coleman had pointed out that if the electroweak vacuum is a false vacuum, in other words, we are in a metastable state, its decay by tunneling to the true vacuum will be catastrophic for reasons I have just explained. You will get a fiery death universe. Now, de Grassi et al. In 2013, with the given parameters, they calculated that even if that happens, the decay time will be of the order of 10 to the 10 years. So that is roughly the age of the universe as it is. So any process which will happen will at least happen at the speed with the lifetime of the universe, and therefore that is certainly more than our lifetime. So we don't have to worry about it at the moment. Then a paper came shortly after, which pointed out that this is only true now. But during the inflation period, the tunneling things were much closer. The tunneling times were much smaller. So this would have occurred unless the Higgs vacuum is a true vacuum. And for it to be a true vacuum, we need new physics. Okay, so since it did not occur, there must be new physics. But again, contradiction came from Espinosa et al., saying that this is true only if you do this in flat space. But if there is a mixing between the curvature and an inflaton field, and the curvature parameter is xi, you can tune xi to keep the vacuum stable throughout inflation. So the vacuum could have been stable all the way, and destabilization is not needed, and therefore new physics is also, you are not sure that it have to come. The last thing in this which I know about is that this group predicted that this calculation ignores the effect of reheating. But reheating will again destabilize the vacuum unless you tune this xi to what is called the conformal point, which is the value of -1.6. So you can have a fine-tuned solution and you could still have a stable universe, but at the cost of that fine-tuning and curvature inflaton mix. So okay, that's not quite new physics, but it's also, in some sense, these are beyond the minimal lambda CDN. Okay, let's come back to the CP finding a solution for CP. So that was pointed out long ago in the 1970s by Pechey and Quinn. So what was the idea? Introduce a chiral symmetry for the quarks with the parameter eta, and then the change in the action would be proportional. You could show that as the del mu of the chiral current, and the chiral current, of course, you can get related to this object by the chiral anomaly. So your new Lagrangian will be this theta parameter. Of course, I assume that that's already there, and then there'll be minus of this term with the chiral anomaly and with the parameter eta in front of it. So if you take theta minus this to be 0, then of course you are planning to cancel out the theta term or rotate it away if you like. However, here, if you do the same thing on the quark fields, then the quark mass term will become a non-trivial space. It won't be invariant, which means that the quarks will have to be massless. Of course, we know they are not massless. So anyway, what was then suggested is that you could make the chiral symmetry local. So instead of the eta parameter, you put an axion field and call it an axion. And then, of course, this is a scalar, treated as a scalar. So there's a scalar, and you have this extra term which is coming from this is the Lagrangian. So I write an integral. So there'll be the axion field instead of eta, and this is some parameter just to keep the dimension. And you have a cancellation as before, but it will be for a specific value of the axion field. Now, do I have to actually fix that? No, that is because this term acts as a potential for the axion. You expand it, it's like a potential for the axion. When you minimize the axion potential, you will get precisely this condition, what we had before. So A by FA, which was eta, is the same eta as you got it. So you fix eta to whatever vacuum expectation you got from here, and that will automatically cancel out the theta term. However, the mass of this axion field, now this potential, of course, once you have the minimum, you can expand it. The next term will give you the mass. And this is proportional to 1 by FA. So you can, of course, tune FA as convenient to whatever you would like to do. The problem is if MA is too large, you would see its effects because the A will couple like the Higgs. So if MA is large, axion couplings are large, and you would see their effects, which you don't. And if MA is too small, what will happen is that this you will get too large a relic density. In other words, you would overclose the universe, which in a way doesn't seem to be closed, it seems to be expanding. So there is some range of
sorry
MAs,
to interrupt, sir.
and that's how you use it.
I have 10 more
Yes.
minutes, sir.
Okay, thank you. So that's it. Then you have dark matter candidates. So dark matter candidates must be neutral, stable, and weakly interacting. The stability can either be due to the particle being very light, so it's kinematically disallowed from decay, or it's protected by some quantum number from decay. For light particles, most of the studies are regarding axions, and you get constraints from various places, cosmology, cooling of red gas, nuclear interactions, and so on. Also, there are the WIMP models with heavy particles. So the most common one is supersymmetry. I think everyone knows how you get R parity, and the lightest supersymmetric particle cannot decay, it will be stable. You can have universal extra dimensions model. I didn't talk about them, but there are models where every standard model particle has KK modes. And there's a KK parity because each of them, which is -1 to the n, which is conserved. So standard models have -1 to the 0, that's 1, and these have 1. So once again, lightest KK particle cannot decay, and it's stable, and it's a dark matter. Then we have the littlest Higgs models, where precision tests will require you to preclude some operators. So you have to introduce a parity called T parity as Z2 symmetry. And once again, standard models have 1, and their partners have -1. So the lightest T particle cannot decay. So you do have candidates for dark matter from here. Now, for dark energy is mostly probed by modifying gravity. It can be Newtonian or Einsteinian, depending on what you're doing. But a particle physics solution can also be thought of. What is the idea? Take the Robertson-Walker metric, and R is your expansion parameter. So you have the Friedmann equation, which describes this. And you have these three parameters here: the matter density, the pressure, and the cosmological constant, which essentially is the wave, the vacuum expectation value. And normally all of these are positive. So therefore, this would actually be cause the universe to shrink. But instead, we find that the universe is expanding. So therefore, you need this to be positive, and therefore you have to get something negative in all of this, in all of these quantities. So which is the one? Matter density, negative energy, negative vacuum expectation value are very difficult. So the one you can attack is pressure. So negative pressure corresponds to a repulsion. So you assume that there is a scalar field which does this job, which has an effect. So the equation of state is such that it seems to be repelling to the others. And this is called quintessence. So once again, I'm being sketchy, but anyway, I won't have a short time. Then we have the solution for electroweak baryogenesis. How does that happen? We assume that in the early universe, there were bubbles of the broken phase versus the unbroken phase. So the broken phase bubbles gradually increased and merged and gave us the present universe. So if you add a singlet scalar to the standard doublet, you can arrange that such that if you have a particle, a baryon, then it can come inside the broken, it can penetrate the wall and come inside the broken phase. But if you have an antiparticle, then it won't come in. It will stop at the boundary and stay in the unbroken phase. Now, in the unbroken phase, since the gauge fields are massless, they can pick up these gauge configurations called sphalerons. And sphalerons end up by converting antibaryons to leptons. On the other hand, in the broken phase, the gauge fields are heavy, so sphalerons are suppressed. So that kind of conversion will not happen for the baryons. Result is that inside the broken phase, eventually you will have an excess of baryons and very few antibaryons. And as these merge and and join to form the whole universe, then you end up with getting a large barrier mass. Okay, but this requires new sources of CPU violations. We've seen that. So there are various suggestions, extra phases in supersymmetry, in composite Higgs boson, a time-varying top U-cover coupling, where the top has a phase and that does it. Two Higgs doublet modulus with a Higgs web, and of course these are time-varying, so they have to be large in the universe. And standard model with time-varying U-cover couplings that can also do it. And finally, CPU violation from a dark matter particle is also possible. So now, of course, we have to look at the experimental tests of these hypotheses. Experimental tests are ultimately what will tell us whether to believe them or not. And as we know, we look at the new physics searches at the LHC and the ATLAS and CMS detectors. And what do we know about that? We simply know that as they have made many searches, detailed searches for gluons, for quarks, for all sorts of bottom, top, charginos, neutralinos, everything has come up negative. All that we have our bounds, which range over the TV, between the TV, so roughly around the TV. We have also looked at our CMS. I'm showing you the CMS results for all other kinds of models, not just this, but many other kinds of models which give you electroweak heavy particles. And everywhere they have drawn a blank. So just taking you through this thing, but the bottom line is nothing. Even the search for long-lived particles as of now, has not shown up any positive results. So what about dark matter searches, which have been done at low energies? The idea is that since we are immersed in dark matter, a dark matter particle comes, interacts with the nucleus, and there's an outgoing particle, and also there are electrons, and they show up in your detector. These experiments, as you show, have only given us bounds. So this is sort of the allowed region. Well, hardly a WIMP anymore, a light particle, and fairly large cross section. Okay, so at this stage, it's clear that the standard model is winning, and beyond standard model, there is no sign of at all. However, let me point out to you that here is an analysis, 2015 analysis of the P, or the phenomenological SSM, and these are the allowed points in different kinds of scenarios. And you see, there are still plenty of allowed points. The data collected after 2015 has sort of may have reduced some of these extreme values here, but there's still plenty, and it's not so early to say that the supersymmetry is ruled out. It isn't. Here is also the question that very light axions, these are bounds on axions, so the white regions are the allowed regions. There are plenty of scope for a reasonably small, of axions of various masses, even heavy and light ones. Even very light axions are allowed. So therefore, the idea that beyond standard model is dead is not correct. So I will quote Mark Twain to you. The reports of my death, he said, have been greatly exaggerated. And similarly, that is true for supersymmetry and beyond standard model. Okay, so now let me just quickly come to the speculation which comes from experimental fuel, because in an experiment, suppose if you see, for example, a dead body and a man with a gun holding it, then clearly that guy has killed him. So that's the smoking gun sequence. So first, let's look at the muon anomalies. And in the muon, of course, you calculate the anomalous magnetic moment at one loop. Then you go to higher, this is the full standard model. There's a QCD correction. When you go to higher loops, the QCD contributes in different ways. And of course, these are all the diagrams we have at 5 loops. All these diagrams people have done patiently. And the result is that you have this theory, which is 10 to the 11th. So the accuracy is down to 10 to the 10 places of decimals. Now the Fermilab G-2, which is continues the Brookhaven G-2 experiment. So they have found an experimental value which doesn't quite agree with the standard model prediction. Note how precise this is, because it's only in these last 4 places of decimals. And the result is that there is a discrepancy, which is about 4.2 sigma. And this discrepancy can be explained by new physics. It can't be explained by the standard model as of now. So either new supersymmetry and so on, there are the models, compositeness of the muon itself, and new hadrons which would contribute to the QCD. So all of these have been considered. Then there are the famous flavor anomalies. The LHCb machine is here. And if you measure the RK, for example, branching ratio of B going to mu plus mu minus by E plus E minus, then you see that there are clearly discrepancies at some level. And the earlier experiments were not accurate enough to do this, but now we do see. Moreover, there are many others. I just showed you RK, but there's a whole series of it. And then you do see large deviations in many of them. This is the standard. And the theoretical, with the theoretical errors, but the experimental errors. So all of these seem to point to a violation of lepton universality. And the effect, we write the effective Hamiltonian for B going to S, L plus L minus in this fashion, as some operators with Wilson coefficients. The discrepancy seems to be in the C9, where the operator 9 is the BL to SL, B to K, and either mu or so. There are two kinds of one. And this can indicate new physics, either with an extra Z prime, with some different hypercharge assignments, or a leptoquark which couples differently to the electron and the muon. Finally, there is the W boson mass. And there, of course, earlier everything was consistent with the standard model, but we have this recent data from the CDF experiment, which gives you a 7 sigma discrepancy. I don't know. We don't know what to say about this. All right, so does it look now that there is a hole in the standard model? Perhaps the standard model is not so standard, and there is a hole through which we can escape and find out the world of new physics. Well, that will have to be done by future experiments. These are past experiments, but the future experiment, one thing we do know is that as we go up in energy, we have been going up steadily over the years, and so the next things will be higher. This is 10 TeV, it will be another order of magnitude above that. Now, just like the Olympics have a motto of faster, higher, and stronger, so similarly, here our analogy is to go up in energy, luminosity, and precision. And this is simply because when you look at small objects, it's like taking a photograph. So what do you do? If you have more energy, then your sharpness increases because the wavelength of your light is decreasing. If you have more luminosity, then your brightness of your image increases. And if you have more precision, then your photographic plate is like having more resolution. And of course, to get a good, the more expensive the camera you take, well, the most expensive one known is about 30 crores rupees today. So the more expensive the machine you make, you will get a better machine. So what are the possibilities? Some of the new colliders which are being thought of are either of the E plus E minus type, or the PP bar type, or the mu minus mu plus. So these are either lepton colliders or hadron colliders. The PP bar or the PP types are the hadron colliders. So what are they? So the high energy LHC, of course, is sure to run. It will happen in about later part of this decade. The Chinese are thinking of building an SPPC. And there's the FCC, which could have different modes, which is being now seriously discussed at CERN. Lepton colliders, E plus E minus, the ILC, well, it has been discussed on and off for many years. We are not sure it's going to happen, perhaps it won't. The Chinese are also thinking of building a similar machine, which would be the Chinese electron-positron collider. And then there is CLIC, which is a linear electron-positron collider, which may happen at CERN. In addition, there's a large program on neon colliders. Possibly they will have neon colliders. This is their logo. There's been a lot of talk of gamma-gamma colliders. I'm not sure that's going to happen. And finally, the technology of the future, which may actually give you desktop accelerators in the future, are the laser wave field accelerators. So just a few nice pretty pictures. The high energy LHC, ILC if it happens in Japan, the CLIC, and these are the various stages. It can go longer and longer as it goes from 500 GeV. So as it goes from 500 GeV to 1 TeV to 4 TeV, if it goes. And the size of this, you can imagine this lake is Lake Geneva, this blue stuff. Then the muon collider, of course, is going to happen next to the Fermilab area. If it comes up, it's being planned next to the Fermilab ring. The Chinese FCB is very similar to these other colliders. In the first phase, it would run from 350 to 1 TeV, and then it might go on. So the electron positron, and then the proton-proton collider will run from 60 to 100 TeV, which is comparable with the FCC. Then, of course, there's the beautiful idea of laser wake field acceleration, which is the fact that a plasma can support electric fields as high as up to 1 teravolt. And if the cavity contains a plasma, then the energy imparted can be a few hundred GeV per cavity instead of what we have now, 100 MeV per RF cavity, which is what you get. So at least 1,000 times more energy, which means your collider can be 1,000 times smaller. The potential to create a high energy tabletop accelerator. So basic idea is the following: a plasma in equilibrium does not have these high fields, but if a projectile passes through the plasma will start oscillating in the wake of the projectile. These wake oscillations will create regions of very high plasma density. So you instead of projectile, you use a laser pulse. So the laser pulse creates these high oscillation density things behind it. And then if you can pop an electron in, so you can trap it in the plasma, and then it could be shot out by this wake field. So the wake field will give you that, will transfer its very high energy to the electron bunch. Of course, the timing has to be perfect. But with this, there's a potential that you could build eventually small tabletop machines with the same energy as you are now getting from these vast energies. So that would be a revolution exactly like the revolution we have seen in computers. Okay, so a few possible scenarios. Please allow me 5 minutes more. I am almost done. So now imagine that you are unwell and you've gone to a doctor and he gives you the following prescriptions. So he says you're a particle physicist, is the patient wants to understand. So one of your things he gives is an antibiotic. Then he gives you a homeopathic medicine. Then he asks you to take some Unani syrup. And finally, he asks you to do some chanting of something as a faith healing. Now, I'm not sure you would go a second time to this doctor. You would think that this doctor is a quack. But the standard model happens to be this doctor. You can see from the names that the gauge theory, the scalar part, the parity violation, and the CP are all completely separate and unrelated things. And we just put them together. Unfortunately, this doctor is very successful. All his patients get cured, at least on the earth. So therefore, if we see the worst case, that we get see only the standard model, then there must be new physics. It can't be the standard. So if we do not find any new physics, we must question the way the experimental data are being analyzed. So we can ask all these questions. Are we messaging out the new physics? Or have our experiments in some way tuned only to see standard model physics? See the new physics. Or is it that our machines are not powerful enough? That's quite likely, that the new physics is still just outside of our reach. Or is it that our analysis methods are not enough? We'll have to ask these questions. Or I don't know, perhaps there may be some basic principle which we have failed to grasp, which has happened in the past for scientists. Let's also look at the best case, that we have discovered a resonance. And in that case, the first question, of course, will be to see if it's a genuine effect, and will remain where more data are collected. Some of you will recall the 750 GeV diphoton and the fact that it disappeared within a year. Once we know that there is a resonance, like the Higgs resonance, then we have to see what are its quantum numbers, spin, and so on. And then try to check which new particles fit these properties. Then, if there is a new particle and a new theory, we'll have to check, is the underlying new physics theory compatible with other data, or is something else ruling it out? And if all of this happens, then we will ask, does this discovery solve any of the standard puzzles which I mentioned before? And if not, then where did this come from? So we'll repeat Ravi's question as who ordered it. And of course, then we will also try to devise complementary experiments to check that this particle exists in other things, and whether the theory, if that predicts other particles, whether those other particles exist. There's an intermediate case when we just get a discrepancy. We don't have a resonance, but we have a discrepancy from the standard model. So the first question to ask, Will visit a genuine effect, same as before, and will it remain? You recall the CDF anomaly, which disappeared when more data were collected. Then we would first ask whether this is due to misinterpretation of the standard model prediction. For example, are the PDFs wrong? Or if we take something like the mu on G-2, is the QCD part properly calculated? Once, if that we are assured that it's really a new effect, then we ask the same question. For which new particles fit these properties? Is this compatible with other data? Does it solve any of the standard models? If not, where did it come from? And can we devise complementary verification experiments? So I come to the end of my talk. I'll just discuss what are the possible trends I foresee in the future. At higher energies, I think the use of effective theories will become much more important, since we will be in the unbroken phase of the standard model. We will be far above the electroweak energies. Effectively, all particles will be massless. We will be in that unbroken phase. Now, in that unbroken phase is just the phase where the use of effective theories becomes most important. So I do see a much greater use of effective field theories. Of course, new technologies for detector robustness will have to come in, because at high energies, the present detectors will simply burn out. And this is a job I expect that our experimentalists must be already working very hard on. As I see the computations, both the theoretical computations and the analysis of data are becoming more and more complicated. Theoretical calculations will go to much higher levels of precision, and this will take a central role. Moreover, the analysis will become more and more dependent on AI and ML. So artificial intelligence and machine learning are going to be the central tools of the future. Already they have become very important. I also expect that more and more ideas will be imported from other branches of physics, in particular astrophysics and cosmology. Already you have seen a fair amount of astrophysics and cosmology goes into our present understanding. But also I think we will get ideas from condensed matter, as we have got before, Rohini explained in the morning, from plasma physics, from things like the multiverse and so on. You got some of that. The important thing is that I believe that particle physics will remain alive so long as there is curiosity about the major puzzles, and so long as there is the possibility of funding experiments to look into it. So on that hopefully optimistic note, I'll finish my talk. Thank you.
Thank you, sir, for very informative and exciting talk. I think we can take a few questions. So if anyone wants to ask, please raise your hand or please unmute and ask. Okay. I don't see any questions. Anyone? Okay.
Well,
maybe let us thank the speaker again for this wonderful talk.
All right. Thank you for listening.
Yeah, thank you. With this talk, we come to the end of this virtual meeting, and so we can stop here, or if someone wants, like from organizers, if anyone wants to say something, we can. Thanks to all the speakers and participants, also to the organizers for organizing this wonderful meeting.
And thanks to all the chairs for doing all the hard work today.
So thanks. So should we stop here?
Okay, since I'm the last speaker, let me thank you, all the organizers, all the session chairs, all the people who have sat through the whole thing. And thank you on behalf of all the speakers for having listened to us. So thank you and good evening.
Thanks, sir.